Hey everyone, welcome back and let's write some more NeetCode today. So today we're going to learn all about one-dimensional dynamic programming. We're going to solve all the one-dimensional dynamic programmings in the NeetCode 150 list. A link will be in the description below and you can navigate to those problems by scrolling down to the one-dimensional dynamic programming section. And these are all the problems that we're going to solve. So we're going to start with the easiest ones and then work our way to more difficult ones. If you want to check out the code, you can do so on the right-hand side. Every one of these problems will have a code solution, not only in Python, but you can choose any of the 4 supported languages, Java, JavaScript, and C++ as well. And if you're completely new to data structures and algorithms, I definitely recommend checking out some of the courses I have available for pro members. There's a 25% off launch sale going on right now. You can get a lifetime access plan, which will give you access to all current and future courses. Pretty soon I plan on doing system design and a lot of other things as well, like full stack web development and a lot more. Okay, without further ado, let's get started now. Hey everyone, welcome back and let's write some more NeetCode today. So today let's solve climbing stairs. So this is going to be another dynamic programming problem, and this is definitely more on the easy side, definitely compared to some of the really hard dynamic programming problems that we've been solving recently. But I still think that this is a good problem to really understand the fundamentals, understand, the brute force, and taking that brute force, using memoization, and then of course getting the true dynamic programming solution. And by the way, if you don't already know, we have been tracking a list of blind 75 questions on this spreadsheet. So today we're going to be solving this dynamic programming one, the climbing stairs problem. So I will be adding the solution once this video is uploaded. And the link will be in the description if you do want to take a look at this sheet. So the problem statement is pretty simple. We're climbing a staircase and it's going to take us n steps to reach the top of the staircase. Every time we take a step, we have 2 choices of how we can take a step. We can either just take one single step, or we can take 2 steps at once. And all we want to know is how many different ways can we get to the top of the staircase. So let's look at the first example, n equals 2. That means we need to climb 2 steps. So we could draw the picture kind of like this, right? So let's say we start over here, right? This is step 0, basically, when we haven't climbed anything. And our goal is to get up here, which clearly is 2 steps, right? So starting from here, we know we can make 2 choices, right? We can take 1 step and that would land us over here, or we could take 2 steps and that would land us over here. So already we're seeing one way is to just take 2 steps, right? That's what this path would take us, right? That's one way we could reach the goal, right? Just taking 2 steps at once. Now, if we ended up taking 1 step, then we would be at this position. So from here, we would have that same exact choice, right? We can take 1 step or we can take 2 steps. Now, clearly, if we take 2 steps, we've gone too far, right? We were only trying to climb 2 steps total, but if we, end up over here, then, that's not going to count as a path, right? So that would not count. But as you can see, if we took 1 step initially, then we could take another single step and that would be another way. So either this is one way we could reach 2 steps, or we could just take a single double step, right? So clearly there are 2 different ways we could climb the staircase, and that's also the result of this problem. And they basically explain it over here. So let's look at the second example, which is basically if we were climbing 3 steps instead of 2, right? So let's look at the drawing. So once again, we're going to do the exact same thing that we did, right? From here, we could take 1 step or we could take 2 steps, right? And so far we'd get here, but remember our goal is to climb 3 steps. So let's continue. So from here, we could take 1 step, which would land us at the result, or we could take 2 steps, which would get us out of bounds, right? That's not what we want to do. So far we have found one way to get us to the result, but let's continue that from over here. Again, we can take a single step, which would get us over here, or we can take 2 steps, which would get us at the result. So now we found 2 different ways we can get to the last step. And lastly, we still have a path to continue, right? We got here by taking 1 step and then taking another single step. So here we have 2 choices: take 1 step, get to the result, or take 2 steps and get out of bounds. So in the end, we see that there were 3 different ways we were able to get to this last step. As you can see, this is getting really hard to visualize with a single staircase. A more easy way would be to get a decision tree to visualize. And at every decision, remember, we can take one step or we can take two steps. So let's try to visualize the problem like that and see if we can notice any patterns. So let's say we're given n equals 5. We're trying to climb 5 steps. So we can consider, just like the previous drawing, that we're starting at step 0 and our goal is to get to step 5. Now remember, at every given point, we have two decisions to make. We can climb one step or we can climb 2 steps, right? And depending on the decision that we make, each of these is going to lead to a different path we can take to get to the result. And remember, all we're trying to do is count the number of ways we can get to that result. So in this decision tree, we're going to keep making 2 decisions at every step. And at the end, we're going to count how many different ways were we able to get to 5 steps reached. So we can get to step 1 and we can get to step 2. Let's just continue drawing out the decision tree. From here, we can make 2 more decisions. We can take 1 step, which would get us to 2. We can take 2 steps, get us to 3. And similar here, we can take 1 step, get us to 3. 2 steps, get us to 4. From here, we can also take 1 step, get us to 3. 2 steps, get us to 4. 1 step, get us to 4. 2 steps, get us to 5. Now here, we can see that we reached the result, right? N equals 5. So this is our first path that we could reach to get us to the result, right? You can see we took 1 step, then we took 2 steps, then we took another 2 steps. So this is our result. Once we get to it, that's our base case, right? We're going to solve this recursively, right? That's pretty much what we're doing. This decision tree is basically recursion, and this is our base case. We wouldn't want to continue if we got here. So here we would return 1. We found 1 way to get to the result. But for the remaining paths, let's continue. So here we could take 1 step or 2. That'd get us to 4. This would get us to 5. So you can see once again, we found another way we can get to the result. So far we have 2 different paths that can lead us to step 5. And here, let's do the same thing. If we take 1 step, we get to 5. That's the result. If we take 2 steps, we get to 6. That means we overshot, right? We went too far. This is another base case. If this number of steps ever exceeds 5, then we're going to return 0, right? We found 0 ways from this path that can reach the result. So now let's continue. Over here, again, we take 1 step or 2, so we'll get to 4 or 5, another path that leads us to the result. And here we can also take 1 step or 2, which would get us 5 or 6. Similarly over here, right? This is another 4, so the exact same thing is going to happen. Do you start to see we're repeating the exact same problem multiple times? How can we better solve this problem knowing that? So now we have another 4. We're just going to repeat the exact same thing that we just did before, right? Take 1 step or 2. We know we're going to get to a 5 and we know we're going to get to a 6. So you can see every path led to the base case except for this last one. So let's complete this. We can take 1 step, which would get 5, or 2 steps, 6. Okay, so now our entire decision tree is complete. So what's the result going to be? Remember, red means we're going to return 0. Green means we're going to return 1. So let's just count the number of greens. 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 different paths from the beginning that could reach step 5. But remember, since we started here, we were asking how many different ways starting at 0 can we get to 5? And then we got to a subproblem. We got to a subproblem of starting at step 1, how many ways can we reach 5? From this decision tree alone, we see that there's 1, 2, 3, 4, 5 different ways we can reach the result. And down 2, if we're starting at step 2, there's 3 different ways we can reach the result. Now, if you solve the problem like this, basically using recursion, and you could probably do it with depth first search, because this is basically a tree. And what would be the time complexity of that? Well, clearly you can see that we have 2 decisions each time. So it's going to be 2 to the power of the height of this tree. What's the height going to be? It's going to be roughly n equals 5, right? You can see that this is going to be the longest path. So that's roughly the height. So the overall time complexity is going to be 2 to the power of n. That's not super efficient, but you can see here, we're repeating the same problem multiple times, right? When we get over here, we're asking how many different ways starting from 2 can we get to 5, right? And down in this decision tree, we found, yes, there were 3 different ways, right? So then when we get over here, why do we have to recompute the exact same thing? Take a look at these two purple blocks I just drew. Notice how this decision tree looks the exact same as this one, because in both cases, we're solving the exact same subproblem. And since we're doing it depth first search, this one is going to be solved first, right? So if we solve this entire problem, what we said was, okay, we found out starting at step 2, there were 3 different ways to get to step 5. So when we get here, why don't we just take that result, store it in memory, store it in DP, or basically this is a cache, right? We're storing it in memory. So then when we get here, we can just say we already know the result of this, meaning that we don't need to draw out the entire decision tree. We're just going to skip that altogether. We're not going to draw this, we're not going to draw that, and we're not going to draw any levels of this tree. So as you can see, I'm eliminating all that repeated work by saving that solution. But that's not all, right? We see over here, we're asking a different subproblem starting at step 3. How many different ways can we get to n equals 5? Well, in this case, it was 2 different ways, right? Notice how this decision tree is the exact same over here, because here we're asking that same question starting at step 3. What's the number of ways? And since we're doing this depth first search, this one is going to end up being computed before this one. So when we get here, we can just say we already know the answer is 2. So we don't need to run through the entire decision tree again. So in this case as well, we can eliminate that repeated work. So I'm just going to cross this entire thing out. And we're not done yet. See over here, we're asking starting at step 4, how many ways can we get to 5? That same problem is over here. Notice how they have the exact same decision tree. This one is going to be computed first because we're doing depth first search. So once again, let's eliminate this repeated work. So now you can see when we do eliminate all that repeated work, this is what our decision tree ends up looking like. And this is roughly O of n. This is linear time solution. Reason being, we're only solving each subproblem once, right? So we know that the first subproblem, the original problem is starting at 0. Then we get a subproblem of 1, 2, 3, 4, all the way to 5, which is our base case, right? So each of these subproblems is just being solved once. N is 5, so overall the time complexity is big O of n. And this is basically the dynamic programming solution where we are caching the result, aka memoization. So we're using memoization. But this problem can actually be solved with a true dynamic programming solution. As you can see, starting at the result, the result of 0 depends on the subproblem, this one, right? And this subproblem depends on another subproblem, which depends on another subproblem, which depends on another subproblem, which depends on our base case. So why don't we start at the bottom, solve the base case, and then work our way up to the original problem at 0, right? Why don't we start at the bottom, work our way up? This is called a bottom-up. This is called a bottom-up dynamic programming approach. So that's what I'm going to show you. We're going to start at the base case and then work our way up. So remember, we're starting at position 0 and our goal is to get to the 5th step, right? Each time we can take 1 step or we can take 2 steps, right? So I'm going to be storing our result in an array called DP. So we're going to have a position in DP all the way from index 0 all the way up to index n, which is going to be our input value, remember? So remember, we're at the base case initially, right? What's the base case going to be? Well, at the last step, if we start here, how many different ways can we land here? Well, that's just going to be 1, right? That's our default value. So now that we solved that, we are able to solve this one, right? Because remember, this problem depends on the subproblem of this. So from here, let's say we're starting here, we can take 1 step, which lands us at the result. We can take 2 steps, which lands us out of bounds, right? So how many different ways from here can we reach the goal? Again, it's going to be 1. And do you notice how this is always going to be the case, even if we had something like n equals 100? So let's say this was actually 100 and this was 99. This would always be 1, right? This is always going to be 1 because it's at the goal. And starting from here, it's also always going to be 1 because we can take 1 step, which would get us to the result, or we could take 2 steps, which would get us out of bounds. So no matter what the input value n is, this is always going to be the case. It's always going to be 1, 1. Next, we're going to get to the interesting part. So then we want to know, okay, how many different ways from here can we reach 5? Well, this depends on 2 subproblems which come after it, right? So we can take 1 step over here or 2 steps over here, right? So, and then we get to the subproblem, right? So from 4, we don't need to continue to figure out how many different ways from 4 can we get to 5, because we just computed that. That's why we're using dynamic programming. That's why we have this array, because we already computed starting at 4, how many different ways can we reach 5? And we also, starting at 5, how many different ways can we reach 5? That's also 1. So what we're going to do in this value is basically take these next 2 values, add them together, 1 plus 1, and then we're going to get 2 over here. And we're going to do the exact same thing for this position too. So we know here we could take 1 step or 2 steps, right? So what we want to do from here, 3, is find out how many different ways can we reach 5. We just computed that, that's 2. And from 4, we want to know how many different ways can we reach 5. We also already computed that, that's 1. So what we can do is take these 2 values, add them together, and that's going to be what we put here. So starting at 2, we can get to 5 3 different ways. And at this point, I bet you probably get the idea. We're going to do the exact same thing over here. So what value are we going to put over here? Just take these next 2 values, add them together. 3 plus 2 is going to be 5. And remember, this is what we were originally trying to compute. This is going to be the result. It depends on only 2 subproblems, which are listed right after it. 5 plus 3, that's going to be 8. So that's the result. If you're familiar with what the Fibonacci sequence is, or the Fibonacci numbers, that's exactly what we're doing right now. We're starting at the base case of 1, 1, adding these 2 values to get the next result. Then we're adding these 2 values to get 3. Then we're adding these 2 values to get 5. Then we're adding these 2 values to get 8. So you may or may not be familiar with it, but that's what we're doing. And you may have also noticed we're using extra memory, right? We're having an entire array size equals n. That's going to be O of n extra memory. But is it actually needed to have an entire array? Notice how each value, such as this one, only depends on the 2 values that come after it. And this one only depended on the 2 values that came after it. So in reality, we don't need to have an entire array. We just need to have 2 different variables. Let's initialize the 2 variables like this. 1 is going to be this position. 2 is going to be this position. Because starting from here, we want to know how many different ways could we reach the result. If we took 1 step, that's why this is called 1. And if we took 2 steps, that's why this is called 2. And we're basically going to be computing this next value, right? And once we compute this next value, we're going to shift our 1 variable over here, and we're going to shift our 2 variable over here. And we're going to keep doing that until we get to the result of 0. And if we initialize 2 initial variables 1 and 2 as values 1, how many different values do we have to compute that come after it? In this case, you can see we have to compute 4 values, right? So basically we compute n minus 1 values. We have to loop n minus 1 times, and then when our 1 variable ends up getting in this position, that's what we're going to return as the result. So this was a really long explanation because we did a lot of analysis, but when I actually show you the code, it's going to be really simple using this idea of 2 variables being shifted n minus 1 times. So as I said from the drawing explanation, we're going to have 2 variables, 1 and 2. Both are going to be initialized as 1. And then we're just going to loop through n minus 1 times. So for I in range n minus 1, and we're going to continuously update these 2 variables 1 and 2. So the first thing I'm going to do is update 1. 1 is going to be set to 1 plus 2, right? Because we're just adding the 2 previous values and then getting the new result. So 1 is being updated, and we would also want to shift 2 to whatever the previous value of 1 was. But you can see that we're updating 1 before we actually shift 2. So what we're actually going to do is store 1 in a temporary variable before we actually update it. And then we're going to set 2 to the temporary variable so that we don't end up setting it to 1 plus 2. We just want it to be set to 1, so we're going to set 2 equal to temp. Once this loop goes through n minus 1 times, we're going to end up just returning whatever 1 happens to land on, and that is the entire solution. We went through so much headache just to get to these 5 lines of code. Hey everyone, welcome back, and let's write some more NeetCode today. Today let's solve minimum cost climbing stairs, and this problem is very similar to another problem that we've solved that's called climbing stairs. steps. And honestly, I think this is probably one of my best videos explaining dynamic programming. I really walk through all the steps from recursion to memoization to dynamic programming. So I will link this video somewhere on the screen or somewhere on the description if you want to take a look. It's very similar to the problem that we're solving right now, which is minimum cost climbing stairs. It's just a slight variation of that other problem. So we're given an integer array called cost, where cost of I is the ith step on the staircase. And if we pay that cost at index I, then we can either climb 1 step or 2 steps from index I. So in this example over here, we're given an array of 10, 15, and 20. What we're told is that if we pay this cost, if we're at this position, right, and we pay the cost of 10, from this position, we can either take 1 step, which will land us in this position, or we can take 2 steps, which will land us in this position, and we only have to pay a cost of 10 to do that. And also, we are told that we can actually either start at index 0 or start at index 1. So we can either start from this position or we can start from this position. And our goal is to reach the top floor of this staircase. So you're probably thinking, okay, let's just start at position index 0, right? Take a jump of 2, which costs 10, right? Because we're taking 2 steps starting from here. So that costs 10. Then we reach this spot and then we're done, right? We've reached the top floor. So therefore the answer is 10, right? Well, not quite, and it's kind of tricky. I think it's really their fault that they word this problem kind of poorly. In this case, the answer is actually 15. Why is it 15? Well, it's pretty simple. It's because this is the last position in our cost array, but this is not the top floor. The position right after that is considered the top floor, which, yeah, they don't really specify that anywhere in the description, which is kind of dumb, but that's the thing. So the reason why the answer is 15 is because, remember, we can either start at this index or we can start at this index. If we start here, then we can take a jump of 2, which will land us at the top of the staircase. It only costs us 15 to do that. Or we could start at 10, take a jump of 2, and then take a jump of 1, which would cost us 30. Or we could, from 10, jump to 15, and then take a double jump, which would cost us 25, 10 plus 15. So clearly the minimum was when we start at 15 and then just take a jump of 2. So then the result is 15. So then your next idea might be, let's just be greedy, right? Why not always, let's start at one of the positions, either this one or this one, and then always take 2 steps, right? Why exactly would we ever want to take 1 step when we could take 2 steps, right? And it costs us the same amount. Well, there's an answer to that question. And let me show you an example, a counterexample of why sometimes we would want to take 1 step rather than 2. The main reason is because maybe if we take 2 steps, there's a value over here, something like 1,000, right? A really big number. And then we'd have to either take 1 step or 2 step, but either way, we'd have to, it would cost us 1,000 if we land here. Or we could take maybe 1 step and yeah, we'd have to pay 15 and then have to pay a 20. And then we could though take 2 steps to maybe a value over here that's really small, like 5, which would skip us a value like over here, which would be 1,000. So you can't really be greedy. And actually the second example down here is another reason, is another counterexample of why we can't always take 2 steps. So let's really try to understand how we can at least brute force this problem, because we've noticed that from every spot we have 2 decisions, right? Take a jump of 1 or take a jump of 2, and we can't just be greedy and take a 2 jump every single time. So let's try every single possibility. And if you've watched any of my videos, you know that we like to do decision trees when we're brute forcing. So suppose we start here, we start at index 0 and we have, 0, 1, 2 to this index, and this index is out of bounds, and that's when we know we've reached the goal and we can stop. So initially we start at 0, right? We can either jump to index 1 or index 2, and the cost if we jumped to index 1 would be 10. The cost if we jumped to index 2 would also be 10. Now, if from index 1, we can either jump once, right, meaning we jump to index 2, or we can do a double jump and jump to index 3. Of course, if we're at index 1, the cost to jump from there is going to be 15, whether we take a 1 jump or if we take a double jump. From index 2, we actually only have one choice. We can take a single jump, which will land us at index 3, which is actually out of bounds. If we take a double jump, we'll get to index 4, which doesn't really make any sense because that's also out of bounds. So in this case, the cost from jumping from index 2 is 20, so we can put that. Now, just so you know, once we reach index 3, which we already have done in 2 of our paths, as you can see, we can't really go any farther from here, right? So what we're going to say is, as we've stopped here, we want to know, okay, we reached the end, right? We want to know what was the minimum cost to reach this position. So one path, if we jump like this, the cost was 10 plus 15, which is 25, right? That's the total cost to reach this. Taking this path, it was 10 plus 20, which is larger. It took 30 to reach this spot. But we're not quite done yet. We know we can't go in this direction, so we're done here, but there's still one node in our decision tree that we can continue to traverse. So from index 2, we can take another single jump and then get to index 3. And of course, that's going to cost 20 to do that. And so the cost is 20. So you can already tell that this is definitely not the solution. This took about, 45 to reach index 3. So definitely not good. You can see there were 3 different ways for us to reach the goal. And among all of these, the minimum was 25. But remember, if we go back to the actual description, the answer to this problem was actually 15. So why didn't we end up with the correct answer? And it's pretty simple, because remember, we were allowed to start at index 0 or allowed to start at index 1. But clearly in this decision tree, we started at index 0. So don't we have to draw another entire decision tree starting at index 1? Well, if you're clever and you take a look at this picture, starting from index 1, don't we already have that entire decision tree? Just look over here, right? We started at index 1 here. Now we did do some work before we got to index 1, but can't we just pretend like that doesn't exist? Can't we just reuse this entire decision tree? Obviously, we'd have to modify the numbers a tiny bit, right? Because when we start from here, the cost so far is not 10, it's actually 0, because we're pretending like we actually started from here, right? And that will be easy to handle for us if we recursively implement this solution. So what I'm saying is, for us, if we started at 1, we'd put a path over here on the right and then get to 3, and the cost for that would be 15, not 25 as we have down here. And the other path where we go left, we go jump to position 2 and then jump to position 3, that would cost us 15 plus 20, which means the total would be 35 rather than 45, right? So not 45 over here, it would actually be 35. The main point of what I'm trying to show you is there's repeated work here, right? If we take this solution as it is, it's exponential because it's a decision tree. Each node is going to have 2 branches, right? Up to 2 branches. And we're going to keep doing that until we get to the base case, right? Which is index 3. So what's the possible height, the max height of this tree? Well, we could have a potential level for every single position in the input array, right? So the height of the tree is going to be n, which is equal to the length of the cost array, right? So n is equal to the length of the cost array, and we know that we could have 2 branches for every single node, so the time complexity comes to 2 to the power of n. But as we just showed, there's a lot of repeated work that we're doing. If we eliminate that repeated work, we can actually get this time complexity down to big O of n. Because what we're noticing is, to solve the original problem, which is what's the minimum cost if we start at index 0 to reach index 3. To solve this problem, we're asking a couple more questions. We're basically solving the subproblem. We're asking, okay, how about to solve this problem, we have to first figure out, if we're starting at index 1, what's the minimum cost of reaching index 3? And to solve this problem, we're asking another subproblem down here. Okay, what about if we start at index 2, then what's the minimum cost to arrive at index 3? So if we cache this repeated work with a hash map or something, so that we don't repeat the same problem multiple times. What I'm saying is, over here, you can see that we start at index 2 and we want to know what's the cost to reach index 3. Well, it turns out that it was 20, right? From 2 to get to 3, it costs 20. So then when we're trying to solve that same subproblem over here, starting at index 2, how much does it cost to get to index 3? Well, it was 20. we don't actually have to run through that because we already solved that problem over here. Right, so that's the main idea of how we can get this to big O of n. The reason it's big O of n is because we have n subproblems. We're asking, okay, from index 0, how long does it take to get to 3? From index 1, how long does it take to get to 3? From index 2, how long does it take to get to 3? So that will be an O of 1 operation for each position in the array, which will be n time complexity. It'll also be O of n memory complexity. And if we take this idea of caching the recursive solution, we can actually get an iterative solution that I'm going to show you now, which will have the same time complexity and, pretty much the same memory complexity as well. So now let's actually go over the real dynamic programming solution, which will actually have a slightly better memory complexity because we can actually use the input array itself that we're given, and we could actually even just use 2 single variables to do the DP solution. Let me show you why. So we noticed that to solve the original problem, right, starting from index 0, what's the minimum cost to reach the out of bounds position or the top of the staircase? We first have to solve the subproblem of starting from 1 and starting from 2, right? So basically this has a dependency of this and this, but we also learned that this has a dependency of this and this, and basically every one of these cells has that dependency. So how about we actually solve this problem from right to left rather than from left to right? Let's solve the subproblems first and then solve the original problem. Okay, so does that mean we're going to start from index 2? We want to know what's the cost for this to reach index 3? Well, it has 2 choices. It can do 1 jump or 2 jumps. The second jump doesn't do anything because it also goes out of bounds, right? The first jump will go out of bounds, so that's enough for us. And what's the cost to reach 3? Well, it's going to be just 20. Yes, that works, so we can just leave 20 here, right? So from index 2 to reach out of bounds, it takes 20. But what about from index 1? Now we kind of get into one of the more interesting cases, right? From here, we can also do a single jump. So then we're asking, okay, if we do a single jump, it'll obviously cost us 15 to do that single jump, but also the value that should be in this position is from index 2, how long does it take to reach index 3? Because then what we can say is, okay, for index 1 to reach index 3, we can just take 15, which was this jump, and then 20, which was the remainder, right? The remainder to reach index 3. So we can, in this position, we can put 15 plus 20. But hold on, because there's actually 2 paths, right? We already handled the single jump case, but what if we do a double jump from index 1? Then what's the cost that we'd put here? Well, we'd put 15 because that's the cost of making the double jump, but then we'd want to also add the value that goes here to that total result, right? Because from index 3, how long does it take to reach index 3? It's kind of a weird question logically to actually ask, but just to make the math work out, the easiest number we can put here is 0, right? Because if we're already at index 3, it obviously doesn't cost anything to stay here. So that's the reason why we're putting a default value here of 0. Now we actually have to look at 2 choices, right? Because one possibility was we go here, make a single jump to 2, and then go to 3, right? The cost of that will be 15 plus 20. Another possibility is we start here and then just do a double jump to this position, right? And the cost for that is going to be 15 plus 0 because there's a 0 here. So we want to take the minimum of both of these values. What's smaller, 35 or 15? Of course, 15 is smaller, so we're going to put the minimum of these 2 computations in this position. And the good thing is it's already 15. And last, we're going to start from index 0. We're going to see, okay, 10 plus the cost, 10 is the cost for making 1 jump. And then from here, from index 1, what would be the cost to do the remainder of reaching index 3? It's just going to be the value that's here, which is already 15. So 10 plus 15 is 25. That's one possibility. The second possibility would be making a double jump. So from here, a double jump, 10 plus 20, which is the value here, is 30, right? So we want to take the minimum of those 2 values. Of course, 25 is smaller than 30, so we put 25 in this position. So now in this array, every single index represents the entire cost it would take from this index to reach the end of the array, or the top of the staircase. From 2, it would be 20, from index 1, it would be 15, and from index 0, it would be 25. Now, what value do we actually want to return? Remember, we can only start at index 0 or index 1. We can't start at index 2, and we definitely can't start at the top of the staircase. So what we're going to return is just going to be what's the minimum of the first 2 values in this array. Of course, the minimum of these 2 is 15, so we can just return 15. As you can see, the time complexity was definitely big O of n. We just iterated through the array in reverse, and the memory complexity is technically big O of 1 because we're just using the input array itself. And you actually don't even need to use the input array. You don't need to write over the input array, because if you notice, as we go in reverse, this value only depends on the next 2 values, and this only depends on the next 2 values. So really, if you wanted to, you could just keep 2 variables in memory rather than even writing over the entire array. And then as you go in reverse order, you could update those variables to the correct values. But it's your choice of how you want to code it up. Speaking of code, now we can finally jump into the coding solution. Okay, so now let's jump into the code. And this is the same example that we were basically working on. And remember, what we wanted was to just have another extra 0 at the end of the array, just to make the math work out easily for us. So that's what we're going to do to this input array. We're just going to append a 0 value to it. And then we want to iterate through this array in reverse order, right? So what index are we going to start at? Well, in the drawing, I started at this index, but remember what we're going to be doing is taking this and then looking at the next 2 values that come after it. Of course, for the last index, or this index that I'm showing, there aren't 2 values that come after it. So we should actually start at this index. And that makes sense for us because we're not actually going to be updating this value, because we're just going to take 20, add it with 0, which doesn't change this value at all, right? So that's why we're going to be starting at this index. How we can get this index is basically the entire length of the array. We know that the entire length of the array minus 1 will give us the last position, right? Length minus 1 will give us this position. So really we can do length minus 3, which will give us this position, which is where we want to actually start at. So we're going to do the length of the cost array minus 3. And this is just how you do it in Python, at least with a for loop. And we're going to decrement. We're going to keep going all the way until we reach the beginning of the array, and we're going to decrement by 1 each time. If you're not familiar with Python, all we're doing is just iterating, starting at this position in reverse order from this array. So remember what we want to do for cost at index I. What we want to assign this to is really the minimum of cost of index I plus cost of index I plus 1, right? Because from here, if we make a single jump, we're going to land here. So we want to add the value at that position that we land at to the original position. The second choice is if we make a double jump. So I'm just going to copy and paste this because it's pretty similar. If we make a double jump, this is what the computation will be like: cost of I plus cost of I plus 2. But if you want to actually simplify this line of code, you can see that since both of these computations have cost of I as the first value, we can actually just remove cost of I from both of these and actually just take the minimum of these 2 and add it to the original value. So we can just change this line to this, right? Take the minimum of these 2 and add it to cost of I. Yeah, that's the entire code. Just iterate through it in reverse order, do the computation, and then the only thing you have to return is the minimum of the first 2 values of cost of I. So cost of 0 and cost of index 1. And the main reason that this works is because we're guaranteed that the cost array is going to have at least 2 values. If we weren't guaranteed that, then we couldn't necessarily do this line over here. But let's run it to make sure that it works. Let me just delete this first line up above so we don't get any errors. And as you can see on the left, yes, the solution works and it's pretty efficient. Okay, let's solve LeetCode 198 House Robber. In my opinion, this is such a good question to understand. Even though it's just an easy question, you can learn so much about dynamic programming from this problem. And you might already know, Google really loves asking dynamic programming problems. And if you want to get started on that, this is such a good question to understand. So we're basically given an array of integers, like many problems, and each integer represents a house, right? So this is a house, this is a house, this is a house. They're all houses and they're adjacent to each other. So it's basically a neighborhood. We want to rob houses to maximize the amount of money we can rob. So why not just rob all of them, right? Nope, there's a restriction. We can't rob two houses that are adjacent to each other. So we can rob this house, but then we can't rob this house, right? So we have to rob this one next, maybe, right? On the other hand, if we rob this one, we can't rob this one and we can't rob this one. It has two neighbors. This might sound really difficult, right? So let's just start out with the brute force approach. Let's imagine if we were trying to get every single combination. Okay, so the first combination is where we pick the first house, right? So let's draw out what the decision tree of that would look like. Okay, so our first decision was to rob the house with value 1. Okay, so next we want to rob more houses, right? But we can't rob this one. So we have to basically get the max we can rob from these two. So does that sound kind of like a sub problem? Yeah, but we'll get there in a minute. So continuing on with just the brute force, right? Okay, so now we want to rob these two houses, right? Well, we can't rob both of them because they're right next to each other. So we can either rob house 3 or we can rob house 1. So this is the decision tree, right? And so along this path, so if we were to rob house 1, right? Let's say we went along this path. Then we can either rob house 1 and 3 or we can rob house 1 and 1. Obviously, we're going to choose this one because that gives us the total, that gives us the maximum, which is 4. Okay, but what if we didn't rob the first house? We decided to rob the second house. So that would be our other decision in our decision tree, right? Rob house 2. Okay, now we have not many choices, right? We can't rob house 3. So the only house left is house 1. So we rob that one as well. So if we went along this pathway in our decision tree, we would get these two houses robbed, and that's a total of 3. But we remember we found this, which was a total of 4, which is greater, of course, so that's going to be our result. Now, this is a very brute force approach. Imagine if we had more numbers here, right? Maybe a 3 and a 4, then we'd have to have like more paths in our decision tree. This could get very complex. So how can we improve it? Can we identify any subproblem? And the answer to that is yes. Let's take a look at the subproblem. So remember, we have two choices. We want to get the max that we can rob from this entire neighborhood. So the first choice is we rob from the first house and then find the maximum from the remaining houses, right? Imagine there's more houses here. There could be a 3, a 4, whatever, right? This is the subproblem. We're finding the max of a subarray of the entire array. The second choice we have is we skip this house, right? If we skip it, then basically we're saying, okay, find the maximum of the entire subarray, not including the first value. So let's actually write out the relationship if it doesn't make sense yet. So if we want to find the max we can rob from the entire array, we have two choices. Rob in this case indicates the max that we can rob from the entire array. So in our first decision, we decided that we were going to rob the first value. So array of index 0 plus rob the remainder of this blue portion of the array. So we're skipping index 1. We're going to rob the entire array from index 2 to the end. So I'll say n is the end in this case. So that's our first decision. If we decided to rob the first house, then we're going to break up the problem into a subproblem. Now we got to rob the remainder of that array, skipping one of the values. If we didn't rob the first house, then we simply only have the subproblem rob every house, skipping the first house. So we start at house 1, not house 0, and go until the end of the array. So this is the recurrence relationship. You might not know exactly what that means, but it's basically a way to break up dynamic programming problems. Notice the result of the entire problem depends on only these two. If we can compute these two, then we have our result. But notice each rob can be broken up into its own subproblem, just like we did over here. So let's actually solve the subproblems now before we solve the entire problem. Now I could do this in reverse order, right? I could say, let's find the max of this subarray, and so on, but it's a little more confusing to do that, so I'm actually going to do it in order. So let's start at the first house. like we've been doing. So if we rob this house, that's basically our base case, right? So we can decide to rob this house. In that case, up until this point, we could rob a total of 1. Okay, now we get to the second house. So what's the max we can rob up until this point? Well, we can decide to not rob this house and only rob this house if we wanted to. Or we can decide to not rob this house and only rob this house. 2 is obviously greater than 1, so I'm going to decide only to rob this house. Next, we get to house 3. This is where it gets interesting. So what's the max amount we can rob up until this point? So we have 2 choices again. We can rob house 3 and we can rob house 1, or we can just rob house 2. The max is obviously if we rob house 3 and 1, and in that case we'd get a total of 4. Now we get to the last value, 1. So we can decide to rob house 1, and if we did rob house 1, then we would want the max we could rob up until these 2 values, meaning we'd want 1 plus 2, because 2 tells us what's the max we can rob from these first 2 elements. We can't include this one because it's adjacent to 1. So one of our choices is 1 plus 2. That's choice 1. Or we can decide to not even rob house 1. We can just get the max of the entire first 3 elements, not including this one. In that case, we have what we would get from the first 3 elements right here. We already computed it. It's 4. So our choices are 1 plus 2 or 4. Obviously, 4 is greater, so I'm going to choose 4. That means we put a 4 right here. And this last 4 means that for the entire array, the max value we could get is 4 if we wanted to rob houses. So we can put a 4 here. But notice how we don't even have to store this entire blue portion. For each value, like for this one, 4, to compute this, we only need to look at the previous 2 results that we computed. And the reason for that is because we could either decide to rob this one and rob the remainder portion of the array, not including 3, in which case we'd have the value computed right here. The other case is if we wanted the max we could rob from the entire array, we could decide to not even include this and just get the max from these 3. And in that case, the value would be stored here. So now let's look at the code. Since we only need to maintain the last 2 maxes that we could rob from, we'll only need 2 variables. So I'll just name them rob1, rob2. We'll initialize them as 0, because if we get an empty subarray, we want to return 0 anyway. So let's iterate through each of the houses we can rob. And now we want to compute the maximum that we can rob up until this value n. So I'm going to compute that in a temporary variable for now, and you'll probably see why. So the max we can rob up until now, in my case, I'm going to say rob1 or rob2 was the last house that we robbed. Rob1 was the one before that. So knowing that, the max we could get would be n plus rob1, meaning there's a gap between the current house and the previous house, or rob2, which includes the previous house. In case it's not clear, this is basically, let me just make a comment to show what I mean by rob1 and rob2. So rob1 is first, rob2 comes second, and then we get some more values, n plus 1, and so on. So if I want to rob n, then I have to rob 1 as well. I can't use rob2. But if I want to do rob2, I can include n because it's right next to it. So when we iterate to the next position, meaning we get here, we want to update rob1 to now equal rob2. So let's do that. And rob2, in this case, wants to be updated to n. So rob2 can now equal our temporary value that we just computed. At the end, we want to return rob2, because by the time we get to the end, rob2 will be equal to the last value, meaning that it will be the max we can rob from the entire neighborhood of houses. This is a problem you can learn so much from. Even though it's an easy problem, it might take you a while to digest exactly what's going on and to understand all the importance of this problem. So many dynamic programming problems are built upon this one. Today, let's solve House Robber 2. We already solved House Robber 1, and I would recommend watching that video or at least solving that problem first before this one, because this one is very similar. So basically the premise of the problem is the same. We're just trying to maximize the amount that we can rob. And in this case, we have a street, aka an array. So this is our array. We want to maximize the amount that we can rob. The only catch is that we can't rob two values that are adjacent to each other because it's like two houses that are together. We can't rob two houses that are right next to each other. We have to choose one. So we can either choose the 2 or we can choose the 3, right? So that's basically House Robber 1. Now there's one more catch with this problem. In this case, the houses are actually arranged in a circle. So we have this as our array, but really this is what our array is going to look like. The 2 goes to the 3 goes to the 2, and then the 2 goes back to the 2, right? Basically what we're saying is this last value is also adjacent to the first value. So it's literally that simple. That's the only difference between House Robber 1 and House Robber 2. And actually the good thing is you can reuse the solution from House Robber 1 to solve this problem. And I'm going to show you how. So let's just remember House Robber 1 first of all, right? So we have this array, right? We can choose the houses we want to rob, but we just can't rob adjacent houses. So I'll explain at least a little bit about how we solved House Robber 1. Basically, it's kind of dynamic programming, and you can watch the first House Robber explanation if you want the basic, like the better explanation for it. But basically, okay, what's the max we can rob up until this point, right? That's 2, obviously, right? So we remember that. Okay, the max we can rob up to here is 2. Okay, what's the max we can rob up until here, right? Clearly, we have to make a choice. We can either rob 2, right, and then nothing from here, right? We don't rob here, and in that case, the max we could rob up until this point would be 2. But we know that rather than robbing house 2, right, we don't even carry this value forward. We just rob house 3, right? So then we can put a 3 here. So up until this point, the max we can rob is 3. Now, lastly, what's the max we can rob up until this point where we're looking at the entire array, right? Whatever value we put here is going to be our solution. So now we have two choices, right? We can rob house 2, skip 3, and then rob up until this point, right? And the value for here is 2, right? So 2 plus 2, we would get 4. Or we can make another choice. We can actually skip this house and just carry over the value that we computed before. What's the max we could rob from here, right? That's 3. We would just put the 3 here. Now, clearly, the first one that we computed was 4, so that's greater. The max we can rob for the entire array is 4. Now, I like House Robber 2 because it requires us to reuse the solution from House Robber 1 in a slightly clever way. It's not even about algorithms at this point. It's more about reusing the solution. It's about, you know, having a function. So the only restriction here, right? You see up here, we robbed, like we were looking at, okay, what's the max we can rob from the entire array? The only restriction here is we can't use the same solution from here over here, right? The max we can rob from the first array is 4 with House Robber 1, but with this, if we rob this, skip this, and rob this, we're not allowed to do that because remember, the first and the last house is connected. Basically, what I'm saying is if we rob house, like the first house, we can't rob this one. Or if we rob this house, we can't rob this one. How can we reuse the solution from up here? Let me show you. Let's say this is our helper function, right? House Robber 1. We can basically say, okay, we can run House Robber 1 on the entire array except the last value, right? And what's that going to give us? It's going to give us a 2, right? We can also run the House Robber 1 helper function on the entire array except the first value, and that would actually give us a max rob of 3. I think for this one it would also be a max rob of 3, right? But basically what I'm saying is we kind of have to run the helper function twice on different subarrays of our input array because we're not allowed to rob the first and the last house together. So if you actually understand houseRobber1, right, the helper function that we're going to use, and you understand what I'm saying over here, right, where we're not allowed to rob both the first and last house, then all you have to do is call the helper function twice on these two subarrays, and whatever one is the max is the value we're going to return. You can see in this case, from the first array, the max you can rob is 3, right, if you rob 3 and skip the first house. And if from the second array, the exact same thing is true because this is a pretty symmetrical array. So if you skip house 2 and rob this one, this 3, you also get a max rob of 3. So that's going to be the solution. But it could have been different technically, right? Maybe this could have been a 5, right? And in that case, the max you could rob from the first subarray would be 5, skip the 3. So then 5 would be our solution, right? And once you can basically identify this problem, it's pretty straightforward. And so since if you might remember, the houseRobber1 algorithm is a linear time algorithm, O of n, all we're doing is calling that same algorithm twice. So the time complexity is going to be big O of n, right? And the memory complexity is going to be O of 1 because we don't really need any extra data structures for the most part. So now let me show you the code and it'll make a little more sense. So first, I'm going to create a helper function, right? Basically, what I'm going to put here is our solution from houseRobber1. If you remember, we have two values, rob1 and rob2. Basically, these store the max amount you can rob from the previous two houses, right? And initially we can set them to 0, right? We can just assume that there's two random houses that come before our input array, and both of those houses are value 0, or however you want to call it. But we are going to have to go through every number in the input array, every house, right? And so how are we going to compute what's the max we can rob up until this point? I'm going to store that in new rob, but you could call it something else. How are we going to compute that? Well, we're going to take the max of the current house that we're at, right? N plus rob1, right? So rob1 plus n, because we're not adding rob2 to this, remember, because we have to skip rob2, right? We can't rob two adjacent houses. We can't add rob1 and rob2 together because those houses are adjacent, right? N is adjacent to rob2. We can't add those together. But this is one solution. We're skipping house 2. Or if we decide we do want to include rob2, then we're not allowed to include rob1 and we're not allowed to include n. The other choice that we have is just rob2, right? So we want the max of these, which is going to tell us up until the current position that we're at in nums, what's the maximum we could rob. So this is the new rob, right? And since we're continuing to iterate through the array, we're going to continue to update rob1 and rob2. So since we're shifting by 1, we're going to assign rob1 to the previous value that was at rob2. And we're also going to update rob2 with the value that we just computed new rob, right? And basically, once we've gotten to the end of the array, rob2 will contain the max amount that we can rob from the entire input array. So after the loop, all we need to do is return rob2. And so now that we've gotten our helper function done, we've basically solved the problem, right? But there's just a couple edge cases you have to worry about. So we're going to call our helper function, right? And remember, one of the cases was we're going to skip the first house, right? So we're going to call the helper function skipping the first house. How can you do that? In Python, you can just say pass in the entire array starting at index 1, right? So we're skipping index 0. So we're skipping the first house, right? So that's one call that we're going to have to make to our function. We're also going to have to make one more call, right? And this time we're skipping the last house. So you can do that in Python like this, right? So -1 is basically the last index, and we're saying we're skipping the last index, right? But mainly I'm calling the helper function, passing in the entire input array except the last house. That's what I'm doing. So we've computed these two values and we want the max of them. So we can just take the max of the values that these two functions return. Now, there's one last edge case we have to worry about. What if we got an input array with only one value in it? In that case, the max of this would end up being 0, right? But that's not necessarily true because we're skipping the first house here, so we're passing in an empty array. We're skipping the last house here, so we're passing in an empty array, right? But technically, a solution could just be the first and only house if we only had one house in our input array. So we're actually taking the max of 3 values here. And one of those values is literally just the first house by itself. So the maximum of these 3 is going to be the max that we can rob. So then we can just return that value. The convenient thing about Python at least is that you can actually take the max of 3 values. And don't forget, actually in functions in Python, you have to put self as one of the first parameters. So now you can see that this is a valid solution, and it's pretty efficient because this is a linear time algorithm, big O of n. And that's all. If this part isn't clear, like the helper function, I would watch the first video for House Robber 1. Hey everyone, let's solve another classic LeetCode problem today, longest palindromic substring. So we're given a string, in this case, BABAD, and we want to return the longest palindromic substring that exists inside of here. In this case, there's actually 2, BAB as well as ABA. So we could return either of these and that would be perfectly fine. Now, what actually is a palindromic substring in the first place? Basically, it means that, you take BAB, if we wrote that in the reverse order, which would be, BAB, it's the exact same string. So, like I usually do, let's say you just don't know how to solve the problem. Well, what's the most brute force way you could do it? Well, you could say, I'm just going to check every single substring in this original string and check if it's a palindrome and get the longest one. Starting at B, so I would check this, I could check this, I could check this, this, and this, right? So every substring containing this original B. And I want to check for each of these, is it a palindrome or not? And I would repeat that process with every character, right? So for this A, I'd get every substring and basically keep doing that. Now, the question is, for a string, for example, BAB, what's the time complexity to even check if it's a palindrome? Well, we'd have to scan through the entire string, right? So for any given substring to check if it's a palindrome, it's going to take linear time complexity. So let's say n, right? Now, how many substrings do we actually have to check? N squared, because we're checking every single substring containing every single character. So to check if a string is a palindrome, we have to do a linear scan, and we have to do that for every single substring. So then that's going to mean that the overall time complexity of this brute force approach is going to be big O n cubed. So the question is, how can we do better? Well, it actually involves understanding how to actually check if a substring is a palindrome or not. For, again, let's look at BAB. We can check if it's a palindrome by starting at the outside and comparing these characters. And as long as they're equal, we'll keep going until we get to the middle, and then we'll check, then we'll know, okay, it's a palindrome. But we could also do it another way. We could start at the middle and then expand outwards and check if it's a palindrome that way. So, well, which one of these is going to help us more? Well, let's think about this. Let's say I wanted to know, for this B, what's the longest palindrome where this B is the center of the palindrome? Well, there's no character to the left of it, so it's just going to be this character, this B itself, right? So it's just 1. What about this A? Well, let's start expanding. There is a character to the left and there is a character to the right, and they happen to be equal. So the longest palindrome with this A at the center is going to be length 3, and it's going to be BAB. Notice how if we do it this way, for each character, we're going to consider it the center, and we're going to keep expanding outwards. We're going to take each character, so that's going to be n, and to expand outwards for each character, it's going to be n again. So for this way, the overall time complexity is going to be O of n squared. So that's kind of clever, right? Like a subtle difference of how we check if it's a palindrome can really improve the time complexity. But hold on, there's one edge case that we're missing. When we take one character and expand outwards from it, like for this B, we're getting palindromes that are of odd lengths. they've conveniently shown us this example where the longest palindrome is actually even. So how are we going to check even palindromes? Well, that's just a slight edge case that we can easily add to our solution. So we just have to remember to handle this edge case when we're implementing our code. Okay, so let's get to everybody's favorite part, the code. So I'm going to initialize the result as an empty string because, that's just a good default case. We'll get the longest length initially set to 0. Now we're going to go through every single character, or rather every single position in this string, considering it to be the center. So first, let's check odd length palindromes. So I'm going to have a left and right pointer. These left and right pointers are going to be initialized to I, which is our center position right now. While my left and right pointers are inbound, as well as while this is a palindrome, so I want to check that the left and right are equal to each other. Remember, we're starting in the middle and expanding outwards. So while this is the case, we know it's a palindrome, so we can potentially update our result. So we'll check that the length of this palindrome, which we can compute by saying right minus left plus 1, is greater than our current result length. Then we update the result. And we also have to not forget to update the result length. I usually forget to do this. And let's also not forget to expand our pointers outward. So our left pointer will be shifted to the left. Our right pointer will be shifted to the right. So now let's check the even length palindromes as well. Right now, you can handle this a bunch of different ways. The way I'm going to do it is setting the left pointer to I and setting the right pointer to I plus 1. So again, we're basically copy and pasting the code that we just wrote above. Maybe we could write a function to do this, but I'm too lazy to do that. So while it's a palindrome again, we'll check that the length is, we'll check that it's the longest palindrome that we've seen so far, basically. If it is, we update our result. And again, we can expand our pointers outward. And at the end, all we have to do is return our result. So I kind of made it look easy with the code, but don't let it fool you. It took me a while to write this before I started recording this. There's a lot of edge cases that can be kind of annoying with this problem, I think. For me, putting the if statement, checking that it's the longest palindrome inside of the while loop helped, I think. If you put this outside the while loop, it kind of makes it harder. But I hope this at least gave you a little bit of the intuition behind the problem. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve palindromic substrings. And this is another problem from the LeetCode Blind 75 list, a list of 75 very good LeetCode problems to solve. And this time we will be doing palindromic substrings down here. And so we are getting one step closer to filling out this entire list. And this problem, palindromic substrings, is actually really similar to another problem I've solved, longest palindromic substring. So if you would like to, I'd recommend watching this video as well, longest palindromic substring. I will probably link it in the description below. So simply, we are given a string S and we just want to return the total number of palindromic substrings contained in the string S. And as you may know, a palindromic substring is basically a string that can be read backwards, and it's the same string. So, A, if you read it backwards, it's the exact same string, right? A, B, A. This is the same string reversed, because the first character is the same as the last character, and then in the middle, we're just left with one character, and basically that kind of pushes us towards a base case. So as you may know, there's two types of palindromic substrings, strings of odd length, right? So for example, just a single letter A, that's a palindrome, right? It's the same backwards. If we add a B to the beginning and a B to the end, it's still a palindrome because now we expanded it outwards with the exact same character. Similarly, we can do the same thing with even length substrings as well. If we have two A's in the middle, then of course this is a palindrome. And then if we continue to expand outwards, we add a B at the beginning and we add a B at the end, it's continuously going to be a palindrome because these characters are also matching. Now, if we, instead of adding a B, we added a C at the end, the inside is a palindrome, this string of length 2. But now if we expand outwards, this is not a palindrome, right? Yeah, it can't be read backwards. C is not the same as B, it's not a palindrome. So that's a little bit about palindromes, even and odd length. But so how can we apply that to our input? So in this case, we are given a string A, B, C. Now, of course, we have 3 different palindromes because each character by itself is a substring, of course, and each of those by themselves is a palindrome as well. So that's 3. Now, is any other substring, for example, AB, that's not a palindrome. BC, that's not a palindrome. ABC, that's also not a palindrome. That's basically all the substrings available to us. So we only find 3, so we're going to return 3. So let's understand how we can do the brute force solution, which is actually big O of n cubed. And then we can actually optimize it a little bit, understanding how even and odd palindromes work. And then we can get a big O of n squared time complexity solution. So let's say we're given a string that looks like this. If we just start brute forcing it, we want to go through every single substring, right? So every single substring starting at this first position would be something like this, right? There's these substrings, right? Then we'd want to go through every single substring starting at this position, which would look something like this, right? In total, there's going to be n squared substrings, right? And for each substring, for example, this one, we need to determine if it's a palindrome or not. And we know, that's not a difficult algorithm to write. We could have 2 pointers, one at the beginning, one at the end. We basically keep comparing the characters and making sure that they're the same, right? So, and for a substring like this, we'd also have 2 pointers, right? Compare that, okay, these 2 characters are the same. So then we can move inward, right? We'd shift our pointers here and then we'd see, okay, this character is also the same. And then, we go through every character. So we determine, yes, that's a palindrome. Then we can increment our count of palindromes, right? We'll call that our result variable. So then we'll add 1 to it, right? Because that's ultimately what we're trying to return, the number of palindromic substrings inside of this string S. And clearly finding and determining that a string is a palindrome is also big O of n. So since there are n squared substrings in the entire string S, and for each of those substrings, we have to determine that it's a palindrome, we're going to multiply it by n. So this is going to give us an n cubed time complexity. Now, we can improve this, and it's going to require us to solve this problem in a different order. What we're instead going to do is we're going to go through every single position in this, right? Instead of finding for this position all the substrings that start at this position, we're going to find all the substrings that this position is the middle of. So instead of, just going to the right, we're actually going to expand in both directions. We're going to go through all substrings where this position is the middle position. Now, clearly, this string itself is one string, right? And this is a palindrome. So we're going to have our left and right pointer just initially at this position. We're going to see that, okay, both of these characters are the same, right? So then we can take our result, add 1 to it, right? So we did find one palindromic substring, and then we're going to try to expand outward, right? Our left pointer is going to go here. Our right pointer is going to go here. Clearly, we go out of bounds, though, to the left, right? So basically what we're saying is there's only one substring where this is the middle position of. And then we're going to do the same thing for here. So from this position, we want all substrings where this is the middle of. So we're going to have our left and right pointer initially here. Yes, this character, our left and right pointer point at the same character. So we found one palindromic substring, just the single character itself. Then we are going to take our left and right pointers and then shift them. So left is going to go over here. Right is going to go over here, right? So now let's compare left character and right character. Since we already know this middle portion is a palindrome, right? Now we only have to compare the left and right characters, the new left and right characters, if they are equal, right? Which they are, A equals A, right? So therefore, we found one additional palindrome, this palindrome of length 3, where this character is still the middle position, right? So now we found an additional palindrome. So I think our total number of palindromes is up to 3 now. And once again, we're going to take our left pointer, shift it to the left, right pointer, and shift it to the right. Now, clearly, once again, our left pointer goes out of bounds. So, we can't really find any more substrings where this is the middle position. But do you notice how, what we just did, right? We cut down on repeated work. We found that this is a substring, and then in another single operation, we found that this is a palindromic substring as well. That cuts down on the repeated work, whereas before we would have done something like, okay, this is a palindromic substring, then we increase it, then we have to look at both of these, and if we continue to increase it, if we go all the way here, then we have to still check, okay, this is the same, and now this is the same, right? We're continuing to do repeated work if we start from the left and then expand to the right. But if we start in the middle and expand left and right, then we eliminate repeated work. So let's do the same thing from here. So this is a palindromic substring, right? Left and right point at the same character. Then we expand once to the left, once to the right. Are these characters the same, right? Are A and B the same? They're not the same. So we knew that the initial substring just in the middle over here, the single character was a palindrome, but when we add this character and this character, it's no longer a palindrome. This is not a palindrome. So no matter what we do now, if I expand one more to the left and I expand one more to the right, even if these characters were the same, assume we had an A in both positions, it doesn't matter because the subproblem, the substring in the middle, is not a palindrome. So therefore, no more substrings expanded from the middle of this position to the left and right. None of those additional substrings are going to be palindromes. So far our count of palindromes is at 4, I believe. So now let's go to the last position. So we want to expand from this middle position. So we're going to go, so initially we're going to say, okay, this itself is a palindrome. So we can change our count of palindromes to 5. We try to expand left and we try to expand right, but again, we go out of bounds to the right side. So we're done. So in total, we found 5 different palindromes, but it turns out we actually missed a couple. We missed this palindrome of length 2, and we missed this palindrome of length 2. How is it that we missed palindromes, and how is it that they're both length 2? Notice how we were starting at each middle position. So this was a length of 1, right? As we add the adjacent positions, then we're increasing the palindrome to length 3, and then if we added a couple more, we'd increase it to length 5. So we're only getting palindromes of odd length. If we want to get palindromes of even lengths, we have to start at every single even position. So we'd have to start at here, and then this is a substring of length 2, and then we'd expand by 1 more, so then we'd get a palindrome of length 4, and etc., just keep increasing it by 2. So this is how we're going to get palindromes of even length. So when we do this, we're going to have our left pointer initialized here, and in this case, the right pointer is actually just going to be left plus 1. Before we were doing it as left and right both starting at the same position. In this case, right is going to be left plus 1. And so in this case, we see these characters are equal, therefore they are palindromes. So we can increase our count from 5 to 6. We expand outwards left and right, but we see left is going to be out of bounds, so then we can stop. So next, we're going to basically do the same thing for every pair of adjacent characters, right, to find even length palindromes. So here, left and right are once again the same, so we're going to get our total to be 7. When we expand to the left and right, we see we have an A and we have a B. These characters are not the same, so we can't continue to expand and we don't increment our result. So now we have 7 palindromes. This is the last even length substring that we're going to start at, and the left and right characters are clearly not the same, so we don't continue to expand and we don't increment our result. So we're done with everything here. We get a result of 7, and the overall time complexity of doing it like this, it's going to be big O of n, because for, let's say, the odd lengths palindromes, we're starting at every single position and potentially expanding outwards all the way to the end of the string. So that's going to be an n time operation. So since we're doing it for every single character in the array, it's going to be big O n times n, right? So that's basically how we're doing the odd length palindromes, and the same time complexity is going to be true for even length, right? We're basically going through every pair of characters, which there are, big O of n of them, and then we're still expanding outwards, so that's also going to be big O of n times n. Now, if you add these together, we're still going to get a overall time complexity of big O n squared. So that's the overall time complexity in this solution. And coding it up is pretty easy, so let's get into that. So let's keep track of a single result variable, and it's initially going to be 0. It's going to be the count of the palindromic substrings. So we want to go through every single position in the string S and expand from it, right? That's going to give us the odd length palindromes. So we're going to initialize our left and right pointers both to be set to I, because these are odd length palindromes. And while left is inbound, so while left is greater than or equal to 0, and right is inbound, so right is less than the length of the string, and the position at left in our string is equal to the position at right in our string, that means we found a palindrome. So let's increment our result by 1. Let's shift our left pointer to the left, and let's shift our right pointer to the right. And we're going to continue to do that while the pointers are inbounds and the characters are the same. Then we're going to continue to increment the number of palindromes. So that's going to give us the palindromes of odd length. We don't have to do a separate for loop for the even length palindromes. Let's just do the exact same thing we've done up above here, except in this case, we're going to initialize left to be I, which is what we did before, but we're going to initialize right to be I plus 1, which is going to give us the even length palindromes. And once we've done that, we can literally just copy and paste this for loop up above down here, and then that'll calculate the even length palindromes. And then once that is done, we can go ahead and return our result. Now, as you can see, this solution works. That's the entire thing. It's very efficient, but maybe your interviewer will want you to, this is copy and paste, and sometimes they don't like copy and paste. We can basically take these two and condense them down into a single function. So I'm just going to do that, even though I'm sure you could probably figure out how to do it. In this case, it's not too bad. So I'm going to make a function called count palindromes, and we'll pass into this the string S and the left and right pointers that we are initializing. And so basically what I'm going to do here is take this and just copy and paste it into here, right? And so you can see that we're giving this function the information it needs. We're giving it the string S. We're giving it pointers left and right. Let's just give it a variable here. Let's declare it. Result is initially going to be 0. And then this function is just going to return result, which is the number of palindromes it can count starting at these left and right pointers. So now we can, change this. So here we were trying to count the odd length palindromes. So instead of doing this for loop, we can just say, let's add to the result whatever this function returns. So count pally, passing in the string S, passing in the left pointer, and passing in the right pointer, which we just declared up above here. And getting rid of this while loop, we can do the same thing. So add to result, whatever this function returns, count pally, passing in S, passing in left, and passing in right. And if we really want, we can take left and replace it with I, and right and replace it with I plus 1. So then we can get rid of these two lines. And up above, do the same thing. So replace left and right with both I, and then get rid of this line. So this is a pretty condensed version of this function. So with this little helper function that we have, we can cut down on that repeated code that we were writing and basically get the same result, same efficiency, same everything. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem Decode Ways. So we're basically given a string of integers, and we want to know with that string of integers, how many different ways can we take that string of integers and decode it into a string of characters. And we're given a specific mapping. So we have 26 characters, and each integer maps to a different character. So we have an integer 1, 2, all the way to 26, and each of these integers maps to a different character. Now, we don't actually need to build that string that we are mapping to. We just have to count the number of different ways we can decode it. So down here in the example, you can see a string like 12 can be decoded in two different ways. One way to decode it is just 1 and 2, because 1 maps to A, 2 maps to B. So that's one string, but remember, we can have double-digit values, so 12 actually maps to its own character. 12 itself maps to 11. So there are two different ways that this string of integers could be mapped to a string of characters, so we return 2 in the output. Now, as you can see, it would be very simple if we just had numbers 1 through 9 that map to characters, right? The problem comes from double digits, right? From 10. 10, a string like this can be taken in two different ways, right? 1, 0, or just 10, right? So that's where the complexity is going to come from. From a string like this, we could have two different decisions. So we're going to be using a decision tree to kind of figure out all the possibilities with this. At least that's going to be the brute force approach. The only problem is that there's going to be a few different edge cases we have to worry about. For example, we could have a string like this. We could have a string like 0, 6, right? What exactly does this map to? Well, 0 is not even in our input, right? Basically, 0 itself does not map to any character, right? 6 could map to a character, but 0 does not. So if we ever get a 0, a string starting with 0, that's invalid. So we have to return 0 in that case. This cannot be mapped to any, this cannot be decoded in any way, so we return 0. Okay, let's try to figure out the brute force approach to solving this problem, and in doing that, we'll try to figure out some of the edge cases that we're gonna have to deal with. Suppose we have a string like this, 1, 2, 1. How many different ways can this be decoded? Well, let's say we start at the beginning, right? We could take 1 by itself, right? That's going to be some character, right? We don't really care what it is, but it's going to be some character. Now, we could also take the first 2 characters by themselves, 12 by itself, right? Because that's valid, right? So that's another decision. Starting from here, we could take 1 or we could take 12. And by the way, if this was a 0, we definitely could not take it. Then we'd have to just stop immediately, right? Because we can't start with a string starting at 0. But if we had something like 1, 0, right, a 10 maybe, then we can take it because it's okay if a 0 comes after a 1. And so basically any integer by itself, right, 1, 2, 3, 4, 5, any integer by itself except for 0 can be taken, right? So basically we can create any string of one number from 1 through 9 except 0, right? We're just not including 0. It cannot be taken by itself, but any from 1 through 9 are okay, right? So what we're going to see here is, okay, if we went down this path where we chose a 1, then the next character we're going to be at is the 2, right? Of course, 2 can be taken by itself, right? Any number except for 0 can be taken by itself. It can be decoded in that way. So when we're at this 1, or when we're at this position, we can take 2 by itself, or we can take 21, right? 21 is also some character. I don't know what it is, but remember we had values from 1 through 26, right? So having a 21 is completely fine. That will decode to its own character, right? Now, of course, if we had something like a 27 over here, then we could not go down this path, right? Then we just would not go down this path because 27 does not map to any character, right? So we're kind of learning that the integers have to be within 1 through 26, right? And this 27 is not. Okay, and so down this path, we reach the end, right? We had a 1 and we had a 21, right? So there's no more characters to choose from here. So basically, this was one way that we could decode this input. So when we reach the end, we're going to count that as a 1, right? That means we found a single way to decode this input. So this was a good base case where we return 1. And from here, let's continue this one. So we left off at 2, then we get to 1. Can 1 be taken by itself? Of course it can. It's not a 0, so we can take it by itself. And so then we reach the end of the string again. So this is another good base case. 1, 2, 1 is a valid way to decode this string. So if we started with 1, over here, we could decode this in two different ways. If we start with 12, how many ways can we decode it? Well, if we start with 12, then we just have one character left, the 1 character. So that can be decoded another way. So this is another good base case. So basically, we saw that we have 3 different ways that we can decode this string. Now, just to kind of add a couple values to this string, what if we had something like 31 after it? So then, let's say we left off over here. we can choose the 3 by itself, right? Because any character except for 0 can be taken by itself. Could we take 31? We could not, right? The same reason we can't take 27. We can't take 31 because it's greater than 26, right? How are we going to determine that in the code? You can do it a lot of different ways. What I'm just going to say is we can only take double-digit values if the first digit starts with a 1. Because if it starts with a 1, then for the second digit, we can take anything from 0 to 9, right? Anything from 0 to 9, because then, this double digit value will either be between 10 to 19, right? And this value is less than 26. So that's perfectly fine. But if we start with a 2-digit, then the second digit has to be between 0 and 6, because 26 is going to be less than or equal to 26. But if this became too large, if it became a 27, that's not less than or equal to 26. So we can't do that. That's how I'm going to decide it. Now, what if the first digit started with a 3, or a 4 or a 5 or anything? That's never going to work, because if we're going to have some other second digit here, it's never going to be less than or equal to 26, right? It just won't be. So we're only going to have 2 decisions, right? We're only going to have 2 branches if our first digit is a 1 or if it is a 2. So this is kind of the brute force approach that I'm showing you, but it might not be super efficient because we could have 2 decisions at every single position. Then our time complexity would be something like 2 to the power of n, where n is the length of the input string. So how can we kind of do a little bit better? Well, notice the subproblem that we're doing. For example, when we take just 1 by itself and consider, okay, this is just going to be one way that we decode it, then we're asking, okay, how many different ways can we decode the remaining of the string, right? That's the subproblem over here. We're asking how many different ways can we decode 21. When we take the first 2 characters, 12, then we're asking how many different ways can we decode the string 1. Right? So that's kind of how the subproblem is going to work. The subproblem is just going to be some portion of the string, for example, starting from here all the way to the end of the string, how many ways can we decode this? Or how many ways can we decode this? Or how many ways can we decode the entire thing, right? To be able to solve this problem, how many ways can we decode this? We have to solve the subproblem, how many ways can we decode everything except the beginning? And so basically, how many different ways can we cache it? Well, we're going to have some index I, which could either be here, or it could be here, or it could be here. It's just going to designate starting from here and taking the remaining portion of the string, how many ways can we decode it? So basically, the dimension of our cache is going to be n, right? So that's also going to be the time complexity, because every time we get to a position I, at most, we have 2 different decisions to make, right? So that's going to be an O of 1 operation making those 2 decisions. It's not like we're going to have to run through a loop or anything like that. We're not going to have any loops, and you'll see that when I write out the code. If this is the size of our cache, this is also going to be the size of our time complexity, and this is also going to be the size of our memory. This is because it's the size of the cache. Now, just so you know, I think this problem actually can be solved when we write out the actual dynamic programming solution, not using a cache, not doing it recursively, but actual dynamic programming. It can be solved with O of 1 memory, because one thing you might notice, okay, when we want to know how many ways can we decode this entire string? Well, when we're at a pointer I, we can either take this character by itself, in which case then we're going to shift I by 1 over here and ask, what's the result of this subproblem? Or if we take the first 2 characters, 12, then we're going to ask, okay, what's the result of this subproblem, right? So we're either going to, basically, to set dp of I, we're either going to ask dp of I plus 1 or I plus 2, right? Those are the only ones that we would need to look at, right? To compute a value like this, we'd only need to, at most, look at 2 different positions that come after it. So, when we have our DP cache, we actually don't need a full array to solve this problem. We could do it with just two variables, similar to like a house robber problem approach to dynamic programming, or like a Fibonacci sequence problem, right? But with that being said, I think we're ready to get into the code now. Now let's write out the code. So the first way I'm going to show you the solution is basically the recursive caching solution, the O of n time and memory solution. So we're going to initialize our cache. We are going to put a single value in here. Basically, the entire length of the string is going to map to 1, because if we get an empty string, we want to return 1 in that case. That's just kind of our good base case, right? And then we're ready to write out the recursive function. I'm just going to call it DFS, pass in a single variable I. Basically, I is the position that we're at in our string S. Now, one base case is if I is in our DP, meaning either it's already been cached or I is the last position in the string, in which case that's our base case, right? And then we would just return DP of I. So that's our good base case. It's either been cached or, it's just the end of the string. Our bad base case is going to be if it's not the end of the string, then we have to check what character it is. If the character is starting with 0, right? If the string is starting with 0, then it's invalid, right? There's no ways to decode a string that starts with 0. So then we have to return 0. So that's like our bad base case. So these are the two main base cases that we have. But remember, if it's not 0, that means it's between 1 through 9, in which case we know we can take this value as a single digit, right? So then the subproblem becomes DFS of I plus 1, right? So that's what the result is going to be. We're just going to call DFS on I plus 1 because we took the character at I as a single digit, right? But we know that there's some cases where we can also call I plus 2. Now, what's a good way that we can write out that case? Well, first, this is one of the ways you can do it. I'm sure there are better ways, but basically if I plus 1 is less than the length of the string, basically if we do have a second character that comes after the current one, right? Because we're looking for a double digit character. So if I plus 1 is in bounds and either the character S of I starts with a 1, right? S of I is a 1 because if it starts with a 1 and there is a second digit, that means that definitely we can take a double digit value, right? Because anything between 10 all the way to 19 is a double digit value, right? So as long as it starts with 1, we know we can make a double digit value. Or the other case is basically, I'm trying to figure out a good way to format this in a readable way, but basically, or if S of I is equal to 2, right? It starts with a 2, but if it does start with a 2, then the second digit, right? S of I plus 1 must be between 0 and 6, right? How can we check that? In Python, at least we can check, okay, if this character happens to be in this substring 1, 2, 3, 4, 5, 6, right? Basically, we're saying is that second digit any value between 0 through 6. At least this is a clean-ish way to write it. So I encourage you to reread this condition if you don't fully understand it, but it's basically what I mentioned in the drawing explanation. We're basically checking if this double digit value is between 10 to 26, so then we can actually take it as a double digit value. If we can do that, then to our result, we're going to add DFS of I plus 2, right? It makes sense we're doing I plus 2 because this is a double digit value. The subproblem becomes I plus 2. And then once we're done with that, we can just go ahead and return the result. But before we do, don't forget to cache it. So DP of I is going to be equal to result. We're caching it, and then we're going to return the result. And then, when we actually want to return the result in the outer function, we can just return DFS of 0 because we want to know how many ways can we decode the string starting at index 0. And I ran it, and as you can see, it works and is pretty efficient. Let me just copy and paste the actual dynamic programming solution. I don't want to waste too much time to write it out because it is very similar. And I think if you can come up with the recursive approach, the logic for the dynamic programming solution is also pretty simple. We have the exact same cache. The only thing is we're doing this bottom up. So we're starting at the end of the string, iterating in reverse order. We have the same base cases. Basically, if S of I starts with 0, then the DP is going to be 0, right? And basically, this is the same as these two lines of code where we just return 0. Else, meaning, that means it's a digit between 1 through 9, then we can call DP of I plus 1. That's the same as when down here when we call DFS of I plus 1. Now, this bottom part is the exact same as the if statement we had down below, right? You can see the logic is the exact same. The condition is the exact same. Only difference is here we're saying DP of I plus 2 is added. Down here, instead of using DP of I plus 2, we actually called the recursive function DFS. So the logic is definitely pretty similar, and in this solution at least, the memory is O of n, but I do think that you can, instead of having an entire cache or array or whatever you're using, you can just have 2 variables. Hey everyone, welcome back, and let's write some more NeetCode today. Today, let's solve another classic dynamic programming problem, coin change, and we get a pretty simple description. So we're given a list of coins of different values, and we're also given a total amount of money that we want want to sum up to. But we want to use the fewest number of coins possible to make up or to sum up to that amount. And it's possible that that amount of money cannot be made up with any combination of the coins that we have, and then we want to return -1 if that's the case. And luckily for us, we're actually given an infinite number of each coin. So in the first example, we have coins of value 1, 2, and 5, and we have infinite quantities of these coins. The amount that we want to sum up to is 11, and basically, just look at this. What's the fewest number of coins we could do? Well, of course, we want to use a 5 because it's the biggest one. We can use another 5, and then we just need a 1 left if we want to sum up to 11. So in this case, you can see we only needed 3 coins. This is the fewest number of coins we needed, so we can return 3. In the second example, we have a coin of value 2, but we want to sum up to 3. We can try 2 plus 2, but we know that's 4, so we went over 3, so there's no way to possibly sum up to 3, so we return -1. There's no possible solution. So your first idea might be, can we just be greedy? Is the problem that easy? Can we just be greedy? And let's look at this example. So let's say these are our coins 1, 3, 4, 5, and we want to sum up to 7. So when I say greedy, I mean, okay, we want to sum up to 7. Let's just start at the biggest coin we have. So let's start at 5. So now let's look at the biggest coin again, 5. If we add a 5 here, we know we're going over the total amount 7, right? So we don't add another 5. Well, let's look at the 4. Well, we know 5 plus 4 is also going to be more than 7. 5 plus 3 is going to be more than 7. Okay, but we found a 1. Luckily, we have a 1. So let's add 1 to it. Now we're at 6. So let's add a second 1. Now we got to the sum 7. So we basically went down from the biggest, smallest coin values, right? That's what I mean when I say greedy. Let's pick the biggest one possible first. So notice that this took us 3 coin values, right? So our result in this case would be 3. But is that the minimum amount of coins? The answer is no, because, just looking at it, we can tell we got a 3 and we have a 4. 3 plus 4 is 7. That means the minimum amount of coins is actually 2. So this is a counter example. We cannot be greedy if we want to solve it. So the next thing you might try is like a brute force solution, right? So to do the brute force solution, we need to implement some kind of depth first search or backtracking solution, right? So let's look at the same example, 1, 3, 4, 5, and amount sum to 7. So what would a backtracking solution even look like for this problem? Well, it's going to be brute force, right? So we have 4 coin values. So that means in our decision tree, we have 4 possible choices. We can choose a 1, we can choose a 3, we can choose a 4, or we can choose a 5. In this case, the remaining amount would be 6, because 7 minus 1 is 6. In this case, the remaining amount that we have to compute would be 4, because we're taking 7 minus 3, which is the coin that we chose. So we get 4 as the remaining amount, right? In this case, we would have a 3, and in this case, we would have a remaining amount of 2. So since none of these are 0, once we get to 0, we know that we've computed the total amount that we want. But right now we have to continue going, right? We have to continue doing the brute force approach. Let's start at this side right now. So we still have 4 coins, right? We have unlimited quantities, so we can choose the coin 1, we can choose a 3, we can choose a 4, or we can choose a 5. If we choose a 1, we'll have a remaining amount of 1. If we choose a 3, we're going to get a -1. What does that tell us? That tells us if we chose a 5 coin and we chose a 3 coin, then we get to a negative value. That means 5 plus 3 cannot be the amount. So we don't have to keep searching here. We can stop, right? We got to a negative value. If we keep adding values to it, it's just going to become more and more negative, right? And you can probably notice that since these values are even greater, 2 minus 4 is going to be -2, 2 minus 5 is going to be -3. 3. So we can't go down these paths either. We don't have to search them anymore. And so now here we're going to see, okay, we can choose a 1 coin. Of course, we can choose a 3, 4, and 5, but we can see from here that that's not going to work. That's going to lead us to a negative value anyway. If we choose a 1 over here, then we know we're going to finally get to a 0. So this is what we want, right? We took a 5 from up here, we took a 1 from over here, and we took a third one, right? So then if we count how many coins we chose down this path, we know we get 3 coins, right? And we get to a 0. So of course we don't have to keep searching anymore. So we found one possible way where we can sum up to the amount 7. We know it has 3 coins, which, from the previous example, we know that that's not the minimum amount of coins, but we found an algorithm that at least tells us a possible solution. So we can kind of keep track of that. The minimum coins we can set to 3. So now I'm going to show you what happens when we go down this tree path, even though we know that the solution is actually 3 plus 4, which is 2 coins, which either of these is going to get us to the correct solution. I'm going to show you what happens when we go down this one anyway. So we can choose a coin 1, 3, 4, or 5. So if we go down this path, we will have a remaining amount of 5. Here we'll have a remaining amount of 3. Here we'll have a remaining amount of 2. Here we'll have a remaining amount of 1. Do you kind of see how we're taking the original problem, which is 7, and then breaking it down into sub-problems like 6, and then breaking it down even further into 5? And not only that, we have sub-problems, yes, but do you also see that these sub-problems are repeating themselves? Here we have a remaining amount of 1. Here we also have a remaining amount of 1. So do we even have to compute this path? Because we already know if we have an amount 1, it takes only a single coin for us to be able to reduce it to the amount 0, which is what we're looking for. So since this subproblem repeats, I don't have to compute it. I can just borrow from over here. So in that case, we see the same thing happened though. We use a coin 1 and we get 0, and we see that, okay, it took 3 coins for us to get to 0, right? We took a 1, a 5, and another 1 from over here. So basically we got the same thing that happened over here, just in a different order. And just to make this a little less messy, I'm just going to tell you that none of these are going to lead us to the optimal solution. So now let's look at this case. We have a remaining amount of 4. How many coins does it take for us to get an amount 4? Well, let's brute force it. Let's check every possible combination. Here we'll get a 1. Here we'll get the value we're looking for, 0, that's great, but let's just look at this last one. With 5, we'll get a -1, meaning we can stop searching. So this is awesome, we got a 0, and let's count how many coins did it take us to get to this 0. We took 1, 4, and we took a 3, so this path is only 2 coins long. We see our minimum is currently 3, but we can actually replace this now with a 2 because 2 is the minimum number of coins needed to total to amount 7. So we know this is the correct answer, but let's just see what happens with the remaining stuff. So first, let me just look at this 1. We see we actually already solved this subproblem over here, so we don't really need to solve it again. We know it takes 1 coin for us to go from 1 to 0. And what about this 3? Okay, well, we can do the same thing, right? 1, 3, 4, 5. And I'll just tell you, from here, we're not going to find the optimal solution. Going from 4 to 3 and more, that's going to obviously be more than the current minimum of coins that we have, which is 2 right now. So this is not going to lead us to the correct solution. But you see that once we compute this stuff, Then we have one last subtree over here, right? This original 3. But once we already solved the subproblems of this, do we really have to solve the subproblems here? No. If we store it in memory, if we have like a cache, or you can call it DP, we do not have to repeat these subproblems. So the way I just solved this was called top-down memoization, because we're doing it recursively, but you can actually solve this with a true dynamic programming solution, which is bottom up. And it means exactly what it says. So bottom up, basically, instead of solving the original problem where the amount is 7, we solve it in reverse order. We start at the smallest one, which is 0, right? This 0 over here. So we want to know what's the minimum number of coins. We can call it DP of 0. So for amount equals 0, what's the minimum number of coins for us to sum to 0? Well, we know it just takes 0 coins, right? What about if we want to know what's the minimum number of coins for summing to 1? Well, we can look at our coins. We got a 1, a 3, a 4, and a 5. These will all cause it to be greater than 1, but we just want a 1, so we can take just this, meaning it only takes us 1 coin to sum to 1. And then we can just repeat that process, right? So for a DP of 2, so we want, how many coins does it take for us to sum to 2? Well, we got 4 coins, right? These 3 will cause it to be greater than 2, so we don't use those. But what about this one? Okay, we get a 1, so it takes 1 coin to sum to 1, but that's something we already knew. So if we want to compute DP of 2, we can take 1 plus DP of 1. Because we know these 3 coins are going to be too big, but we have a 1 over here that's value 1, and we also know that that's not enough, right? 2 minus 1 still leaves us with a remaining amount of 1, but we just computed that up here. We know for us to get the minimum number of coins, to get a value 1, it only takes 1 coin. So that means that if we want to get amount 2, it takes at least 2 coins. And let's say we repeat this process for all values, for all amounts from all the way, starting at 0, all the way to 7 over here. So I computed it from all the way from 0 to 6, but the last one we really want is amount equals 7. So let's compute that, DP of 7. How do we get it? Well, we still kind of have to check every single coin. So what happens if we get coin 1? Then we take the result of 1, meaning that's how many coins we use, not the value 1, because we needed 1 coin with a value 1, and now we have a remaining amount of 6, right? DP of 6. So how many coins did it take for us to compute DP of 6? Well, we already computed that. It took 2, so we get 1 plus 2 equals 3. So that's one possible solution. But is it the minimal solution? Well, let's look at if we use the coin value 3 over here. Well, it takes us 1 coin, so we take 1 plus DP of 4 because that's the remaining amount we have to use if we take a coin value of 3. And luckily, we already computed DP of 4. It is 1. So then we get 1 plus 1 equals 2. And we know that this is the real result that we want. But even before we know that, we would repeat this process. So technically, if we do the bottom-up dynamic programming solution, we are going to repeat this for the remaining 2 coins. So for 4, we would get 1. So we'd have 1 plus DP of 3 because 7 minus 4 would leave us with a remaining amount of 3. And in that case, we know DP of 3 is 1. So we would have the total of 2 again. So we see that there are actually 2 solutions. And we know we have one last coin that we technically have to check, coin 5. So we'd use 1 coin for value 5, and then the remaining amount we'd want to compute is dp of 2. And we know that dp of 2 is value 2, so this would result in a 3, which is not what we want, right? So from these 4 values that we computed, we want to take the minimum, which we know is 2, so we can return 2 in this case. So that took us forever, but luckily the code is a lot shorter. So just like we showed, I'm going to have a dp array, and I'm going to initialize this to be length of amount plus 1 because we are going from 0 all the way to amount. And the default value I'm going to give each element in this array is amount plus 1, or you can do like infinity or whatever the max int is, like math.max integer or whatever in your language. But amount plus 1 is basically a max value anyway. And we know that the base case for this is a dp of 0, meaning if we want to compute amount 0, that it only takes 0 coins. And now we're going to start computing every value in dp. So for every amount a in range, and we're going to do this in reverse order, or rather bottom up. So we're going to go from 1 all the way to the amount. And we technically are still doing it in a brute force way. So we are going to go through every coin. So for coin in our list of coins, so we're trying to compute this A amount. So we're going to take A and subtract the current coin that we're looking at. If this is non-negative, so if it's greater than or equal to 0, that means we can kind of continue searching, right? So this means we possibly found a solution for our dp. So for this amount A, we're going to set it to the minimum of itself and 1 plus dp of A minus C. So this 1 comes from this current coin that we're using, C, and dp of A minus C comes from, for example, let's say our coin value was 4 and our amount that we're trying to compute A is 7. Basically, we're saying dp of 7 is equal to 1 plus dp of 3, because 7 minus 4 is 3. So we're saying that this is a possible solution. And actually, that's the only thing that we have to do. This is basically it. This is like what's called the recurrence relation. And so now the only thing we have to do is return what we're looking for. So dp of amount. So this is what we have to return. But we remember one last edge case. If we could not compute the amount, meaning so we can only return this if the value that's stored is not the default value. So if it's not equal to amount plus 1, right, which was the default value that we gave it. So we'll return this if it's not the default value. Otherwise, we're going to have to return -1, meaning we could not compute this amount with the given coins. So this solution does work, and even though it's pretty efficient, the time complexity is actually big O, the amount that we're given, multiplied the number of coins that we're given. And the memory complexity is big O amount, because we see we have a dp array that we're having a potential value for every single amount. Hey everyone, welcome back, and let's write some more NeetCode today. Let's look at maximum product subarray. And this is actually a dynamic programming problem, and I'm going to show you how to solve this problem easily. So we're given an integer array of numbers, and we want to find the contiguous subarray that contains at least one number and has the largest product. So in this case, we have a 2, a 3, a -2, and a 4. And the largest continuous product we can make is 2 and 3 because 2 times 3 is 6. That is the largest product. We can't really make it bigger because there's a -2. If we multiply this by -2, it's going to be -12. That's not bigger than 6. So what's like your first idea how to solve this problem? Maybe brute force, right? Is there a brute force solution to this? Well, we want to find a subarray, right? So why don't we just try every single subarray? So let's say all subarrays starting at 2. We got 1 subarray, 2 subarrays, 3, 4, right? And for each of these, let's just calculate the product, right? Like the first one is 2, the next one is 2 times 3, the next one is 2 times 3 times -2, the last one is 2 times 3 times -2 times 4. And we end up seeing that so far the biggest is this, but we're technically not done yet. All of these subarrays contain 2. So now let's look at all subarrays containing 3. So we got 1, right, just 3. Then we got 3 times -2. Then we got 3 times -2 times 4. And basically we repeat this process. Now you can tell that this is not super efficient. The time complexity is big O n squared. For each of these numbers, we're going to end up having n subarrays, and we see that the total number of elements we have is also n, right? It's n elements in the array, so we're going to get n times n is n squared. So my question is, can we do better? And how can we do better? Maybe there's some patterns to this problem that we can use to our advantage to find a better solution than n squared. So let's look at one example. Do you notice anything about this subarray? Well, all elements are positive. So what does that end up doing? Like, this is all positive, so we got a 1, okay? And next we want to check this subarray, okay, multiply it by 2. We want to go even farther, check the 3, okay, multiply it by 3. And what if we kept having positive elements? 4, 5, multiply by 4, multiply by 5. Do you notice something? Up until this point, our product is going to be a 1. Up until this point, it's going to be a 2. Up until this point, it's going to be a 6. Up until this point, it's going to be a 24. Up until this point, it's going to be 120. If we have positive numbers, no matter what happens, they're going to keep increasing, right? So this is the simple case. If we get all positive numbers, then our product is always going to be increasing. So now let's actually look at the opposite scenario. What if we had all negative numbers? Because all positives is easy. You just multiply all of them and you get the max product. But with negative numbers, it's a lot more tricky. So let's look at the first number. So up until here, the max product is just -1. And then we add a second element, a -2. And then what do we get? We get -1 times -2. And we know that the product of that is 2, right? Positive 2. Now the last subarray we check from all the way from -1 to -3. So we introduce one more value, a -3. And now if we multiply all 3 of these numbers together, we see that our product actually got smaller. Now it's -6. And what's going to happen if we had another element over here? What if we had a -4? Then we multiply by -4, and now we see that our product is going to be 24. So you see that when you have negatives consecutively, the sign is alternating. So when you want the maximum, it makes it kind of tricky to have negatives. But we also see that even though we got a -6 over here, there's actually a subarray that has a better solution. If you just take these two numbers, -2 times -3, we get a +6. So why did we get a -6 over here? How can we find the real maximum, which is +6? So even though we're looking for the max product subarray, we're actually also going to need to keep track of the minimum as well, and I'm going to show you why. So first, do you at least agree with me that if we want to find the max product array subarray of this, of the entire thing, it might be helpful for us to at least solve the sub problem, which is the max product subarray of just the first two elements first, and then use that to get the entire one. Okay, that makes sense. We know that the max product subarray of this is 2. Now, if we had a positive 3 over here, then we would say, okay, if I can get the max subarray of the first two elements and multiply it by 3, I'm going to get 2 times 3. It works when these are positive numbers, but we actually have a negative 3 over here. So I'm going to say, get the max product subarray, which is positive 2, but let's also get the minimum product subarray of these two as well. And what do we know about the minimum? What's the minimum product subarray of these two? It's going to be negative 2. So I'm going to keep track of both positive and negative. So we have a positive 2 and a negative 2. We keep the max and we keep the minimum. So now when we want to compute the max product subarray, when we include this 3, then we can compute that. We can compute that using both of these values. So we know that when we take the maximum 2, we get negative 3 times 2, which is negative 6. And we know when we take the minimum, we get negative 3 times negative 2, and that gives us a result of positive 6. So we know the maximum is positive 6 and the minimum is negative 6. So we take positive 6 and put it over here, and we can take negative 6 and put it over here. And hypothetically, maybe we get another element, and this time whether it's positive or negative, right? So in this case, let's say it's a negative 4, we will be able to find the solution because the minimum, or rather we're looking for the max product subarray, and we know if we take negative 4, multiply it by the current minimum, which is a negative number, negative 6, we will end up getting 24, which is what we're looking for. But if you reverse it, what if we had a positive 4 here instead? Well, in that case, we can say, okay, positive 4 multiplied by our maximum, right? Our maximum, which is positive 6. So 4 times positive 6, we get 24. We still get it, right? So this, if we maintain the maximum and the minimum, we have all the information we need as we continue to add more elements to our array. So now let's just look at one edge case. So we're talking about positive numbers and negative numbers, but we know that one last edge case exists, the dreaded 0 value, right? So what if we had a 0 value and then maybe some other numbers, 3, 5, our 0 is gonna kind of kill us, right? It's gonna kill our streak. Like, look what's gonna happen to our min and max. If we take 6 multiplied by 0, we get 0. If we take negative 6 multiplied by 0, we get 0 again, right? X times 0 equals 0. And then if we try taking this 0 and making it a product of maybe 3 and 5, it's going to continue being 0, right? Because any number times 0 is going to be 0. So I'm going to decide to handle this in a different way. So anytime we get a 0 value, I'm going to reset our max to 0, or rather to 1. And I'm also going to reset our minimum to 1. And the reason I'm going to do this is because I don't want to kill our product, right? I'm just going to say that zeros are ignored. We don't really care about zeros. And the reason I'm setting this to 1 is because then when we start introducing new values like 3, it's just going to be 1 times 3, right? Which is going to end up being 3. So 1 is like a neutral value for us. So those are the main things. We want to maintain the max and minimum of our product, and we want to handle the 0 case by resetting everything to a neutral value like 1. Okay, so now let's code it out. I'm going to say our result is initially just going to be set to the max value contained in nums, because we at least have to set it to some value. We can't just initialize it to 0, because what if we had an array with just one number and it happened to be -1, right? In that case, this is our max product, which is even less than 0. So 0 is not a good default case. And I'm going to maintain the current min and the current max, and I'm going to initialize these to 1 each, because we know 1 is like a neutral value. And then we're just going to start iterating through every single number in our input array. We know that if we ever get to a 0, we do not want to handle that. We don't want to add that as a part of our product. So we don't want to mess up our current min and max by multiplying it by 0, because then it's going to stay 0 forever. So instead, what we're going to do is we're going to reset our min and our max to 1 each. And we're just going to continue to the next iteration of the loop. If this doesn't execute, that's when we're going to actually do our code and recompute the current min and current max. So our current max, how are we actually going to compute it? Well, in Python, it's really convenient for us, because we can say, okay, the current max could potentially be the new number that we just found multiplied by the current max. If the current max happens to be positive and n is positive, it could also end up being the input value n multiplied by the current minimum, right? What if n is negative and current minimum is negative? Then this could end up being a positive number, which could be our current maximum. The third option is n itself, because what if we had an input such as -1 and 8? Well, in that case, the current min and max is going to end up being -1, and either of those numbers multiplied by 8, which could be our hypothetical n value, it's going to end up being -8. So 8 it's by itself, which is n, is the maximum. And the fun thing about Python is that, look, we just put 3 values into our max function. Some languages don't allow for this, but there's obviously ways to get around it. And so now that we have our current max, we can do the exact same thing for our current min. So min. So we can actually take all 3 of these values, copy and paste them, and then put them in the min, because we want whatever the min containing n is, and it could be anything. It could be n times current max, n times current min, or n itself. So an example would be -1 and -8. If we multiply these together, we get a +8, but we don't want that. We want the minimum, which could be just -8 by itself, which would be this third case. But this is where I always end up with a bug. So do you see how we actually recomputed the current max, but we want to use the old current max? So I'm actually going to have a temporary variable up here, temp. And before we end up reassigning current max, I'm just going to compute current max times n and then save it in temp, so then we can use it down here. So we're going to replace this with temp. So this way we're always keeping track of what the current max is and what the current minimum is. And so we can update our result after each iteration of the loop. And we want the max product, so we can take the maximum of result itself, because result could still be the max, current max, and current minimum. So that's actually it. Like, we've done it, and we can now just return what our result is. And so this is actually not that much code, and it's not even, like, when you look at it, it's hard to recognize that it's even a dynamic programming problem, because it's not like we're storing an entire array like DP and then having an array. We're just maintaining 2 values, current min and current max, and what they tell us is, for let's say, for example, we were at this value n, then we're going to have the current maximum of this subarray and the current minimum product of this subarray. And then when our n gets shifted to the next value, we're going to have the current maximum of these 3 and the current minimum product of these 3. And then by the time our n value is out of bounds, we will have the current max and the current minimum of the entire array computed. So it runs efficiently, and that's because we're only iterating through the input. So instead of being n squared, the time complexity is just big O of n. The memory complexity is big O of 1 because we are not using an array. We're just using. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem word break. So we're given an input string and a dictionary of strings called wordDict, and we want to return true if and only if S can be broken up into separate strings such that every separate string in S is also found inside of our wordDict. And we are allowed to use words from the wordDict multiple times. So for example, let's say we're given an input string LeetCode, and we're given a word dictionary of words called leet and code. So obviously, in this case, we could split this string, right, into separate strings, leet, right, break it down in this middle position, and then the second string would be code, right? So clearly, this can be broken up into words that are found in the word dictionary, so therefore we are going to return true. Now, what if we took code outside of our word dictionary? Well, then in that case, this portion, leet, is a word, right? But we have no matching word in our dictionary for the remainder code. So in that case, we would have to return false. And, let's say we had an input string instead called leet and leet again, right? So two leets in a row, would we return true? Yes, because we're allowed to use this word from our word dictionary multiple times, right? Clearly it matches this, and it also matches the first portion. Now let's start off with the brute force approach. How would we even structure a brute force solution? Well, there's actually two ways to do it, but one of them happens to be more efficient, and I'll tell you why. So one thing we could try for an input string like this one, we could check, okay, the first character, right? Basically the first prefix of this string, L by itself, right? Is this a word that's found in our word dictionary? It's not, right? So let's try maybe the first two characters together are a word, right? That's not it either. We would try the first three, right? Basically, we would try every single portion from the beginning until we found a matching word that does exist in our word dictionary. And we know that we are going to find one like this, right? The first four characters of the string are a word, right? So once we found that, what are we going to do? Clearly, we have a sub problem, right? We found a matching word for this portion, but now we want to know, can we break up the rest of this string with words from our dictionary? So that's kind of how we're going to do it, right? That's what's going to be the sub problem, basically. So instead of starting from the first position in the string, we would start at this position in the string and try to word break it. Now in this approach, what we're going to basically be doing potentially is from every single starting position, right? We're going to check every prefix, right? So from the first starting position, we might also get, if this happened to be a word, then we would start at this position and then do the same thing for this, right? Every word starting here. So basically we're going to try every word. How many different words are we going to end up trying? We're going to try, let's say n is the size of our string n, and we're going to try basically from every single starting position to the end. So that's going to basically be n times n. Now, we could also do it a different way. Instead of trying every single possible, prefix, let's just check every word in our word dictionary and see if that matches. For example, this first word is 4 characters long, right? So what we're going to do is we're going to check the first 4 characters in our string. Does this match this word? Clearly it does, right? So what does that tell us? That tells us now, we have the same sub problem as before. We're going to start from this next position now, right? And check. And from here, we're basically going to be doing the same thing, right? So we're going to check, is leet basically, the first 4 characters, does that match leet? This does not match leet, right? So now let's check the next word in our word dictionary and check, does that match the characters over here? It does, right? We found code. So this is basically another way to do this problem. Instead of checking every single possible prefix, right, of any length, what we're going to be doing is we're going to be checking every single word in our word dictionary as the prefix. So instead of being O of n times n, we're going to be doing O of n because potentially we are going to be going through every single starting position, but we're going to be multiplying by the number of words in our word dictionary, which is, let's call it m, And the reason why we're going to be doing this approach is because it's going to be a little bit more efficient. And the reason is they tell us below in the problem statement that the max size of word dictionary is going to be smaller than the max size of the string. So this is overall probably going to be more efficient. Now, this isn't going to be the overall time complexity. We are actually going to multiply it by another n, because when we're checking, for example, this string, when we're checking, does that match the first 4 characters here? That's also a n time operation, because it could, potentially be the size of the input string s. So this is basically going to be the overall time complexity, n squared multiplied by m. So I'm just going to basically show you the same formula that I usually do. I'm going to give you a quick illustration of what the decision tree would look like. Then we're going to understand how we could cache that to eliminate repeated work. And then by understanding that, we're going to go to the optimal dynamic programming solution, the bottom-up approach, and then we're going to code that up. Usually the DP solution is a lot less code than caching. So we're going to be looking at our input string NeetCode. So I think that's a little bit better than NeetCode, wouldn't you say? So what the decision tree is going to be is we're going to start at the first position, right? For example, I equals 0. We're going to be keeping track of whatever index we're at, right? Because we know that if we can find a word, that matches neat, for example, then the subproblem is going to be finding words that can match the remainder of the string. For example, if we did that, our I, instead of starting at index 0, would basically be starting at index 4, right? So that's what the subproblem is going to be. So really, we're only going to have one variable that we're keeping track of in this backtracking solution. And so remember, we mentioned we're not going to be doing it like this. We're not going to check every single prefix. We're going to have decisions in our decision tree based on the number of words that are in the word dictionary. So we're going to have a decision for neat, we're going to have a decision for leet, and we're going to have a decision for code. Now, what we're going to notice is when we try leet on here, right, basically leet is 4 characters, therefore we're going to check the first 4 characters of here, compare it. Does that match leet? It does not, right? We're just 1 character off, that first one. So basically, that means we're not going to continue down this path. Now, let's try code. Does code match the first 4 characters? Definitely not. So we're not even going to continue down this path either. Of course, neat does match this, so we are going to continue down here. We're going to do 3 more decisions, basically 1 for every single word in our word dictionary. Now, one thing though is when we are starting here, we know we matched the first 4 characters, so by this point we are now going to be at I equals 4, meaning we're going to be looking at this part of the string. So as we can see, checking neat, that's 4 characters long, so let's check 4 characters starting from here. That's not matching, of course, so then we're not going to continue here. Leet, does that match over here? Nope, we're not going to continue down this path. Code, does code match this portion? Yes, it exactly matches. So therefore, we are going to update our I pointer again. Since we matched 4 more characters, we're just going to take I and add 4 to it now. So now I is going to be at 8, and 8 happens to be that exact position right after the end of the string, right? This is where index 8 is. Therefore, we basically know that we were able to match the entire string. Therefore, we know we can return true, right? Once we find a single true, that means we just terminate, we end the function, we can just return true, and the function is done. Now from this example, it might not be super intuitive why we would use a cache, but let's say we had another path in our decision tree that led us to, for example, index I equals 5, right? And let's say we used all 3 decisions in that path, and let's say none of them yielded the correct result, meaning we were not able to word break this string from starting at index 5. So then we would return false from this path, right? And we would want to cache that. We would want to say that, let's say DP of index 5, right? We would want to set that to false. Basically, what we're saying is if we ever reached this same function call, if we ever tried it again, maybe, this decision tree could be really big. Maybe there would be another path from, somewhere over here where we tried index I equals 5 again. In that case, we would want to return false immediately because we saw from here there was no possible way to break it down. Therefore, we don't need to redo all of that work if we, try the same exact thing. So we discovered that our base case is going to be DP of 8 because 8 is the length of the string, basically is going to be true, right? If we can ever get to that last index, we're going to return true. So what we're going to do is now do the bottom up approach, right? we're going to go through every single index in reverse order, right? So we would start at the last character, which is position 7, right? And see, can we word break the remainder of this string? And we would try every single word, right? Like neat, does neat match this string? Well, they're not even the same size, right? If we tried to match neat on 4 characters starting from here, we would go out of bounds of this string, right? There's not enough characters. So of course, this is going to be false, right? It wouldn't match neat. It wouldn't match the other 2 words in our dictionary either. And that's obviously going to be true for DP of 6, DP of 5, as well. So both of these are also going to be false, right? Basically, if we started from 6 or if we started from 5, we would not be able to match any of the words in our dictionary. But now if we start here, index 4, so we're now trying to figure out DP of 4, is that true? Well, yes, it is, right? It doesn't match neat, it doesn't match leet, but it does match code. So we are going to set DP of 4 equal to true. So now let's keep doing it until we get to the first character. So now we're going to be trying from DP of 3, right? So starting from this character, are we going to be able to match any of these? Well, none of these words even start with a T, so of course we're not going to be able to match. So DP of 3 is going to be false. What's DP of 2 going to be? It's also going to be false because if we were to start at this character, this E, would we be able to match any of the words in our word dictionary? Of course we would not. And what about this position? If we started here, would we be able to match any of the words in our word dictionary? Again, not. So DP of 3, DP of 2, and DP of 1 are going to be false, meaning we cannot word break this string if we start at any of these 3 positions, basically. Now we're finally at the result that we were looking for, DP of 0. Is DP of 0 going to be true? Well, let's take a look. So we're starting at the first character in the string. Can we match any of the strings? We can't match leet, we can't match code, but neat, it does match this portion of the string starting at index 0. So then the question becomes, we're asking, can we break the entire string starting at index 0? So now since we did match the first 4 characters, we want to know, were we able to match the remainder of the string, right? So we want to know, starting from here, were we able to match this string to words in our word dictionary? Now, this is why we computed this bottom up, right? Because this is index 4, right? Notice how we already computed index 4 over here, right? It's the one that's highlighted in green because it was true. We were able to do it. So basically the equation that we would use for this is going to be DP of 0 plus the length of the word that we were able to match with. And we know the length of the word neat is going to be 4. So basically we can replace this length of the word with 4. So 0 plus 4 is just DP of 4. We know that was true. So we can set DP of 0 equal to true. So this is basically the result, right? This is how we're going to compute it, and this is what we're going to assign DP of 0 to. And once we've done that, we've computed the result. We know we can return true for the overall function. So with that being said, let's jump into the code. So our cache is going to be, let's say, a one-dimensional array, right? Because for every position I in the string S, we are going to have a value. So we're going to initialize this to false. It's going to be the length of the string S plus 1 for our base case. And we are going to initialize our base case. We know that it's the last position, basically the position out of bounds of the string. So the length of S, and we know that's going to be set to true. That's our base case. So now we're going to go through every position I in the length of the string, starting at the last index and working our way to the beginning. So that's why I'm using the decrementer of -1, and we're going to go up until the beginning of the string. And for each position I, we want to try every single word in our word dictionary and see if the word matches this portion. So first we have to see if starting at position I, the string S even has enough characters for W to be compared to it. So what we're going to do is we're going to check I plus the length of W, and we want to know, is it less than or equal to the length of S? If that's the case, then that means there are enough characters in S for us to compare them. So that's exactly what we're going to do. We're going to, if this is true, then let's compare. So we want to know if that's true and if S starting at index I, going up until I plus the length of W. So basically, let's say W was 3 characters, then we want to know the first 3 characters in S starting at index I, are they exactly equal? If they are equal, then we want to know, okay, so dp of I is going to be set to dp of I plus the length of W, right? That was the relationship we got, I plus the length of whatever the word happens to be. Now, if we got a single way to word break this starting at index I, that means we can basically stop this loop, right? We don't have to look at every single word in the dictionary. If we found at least one way we were able to word break it, then we're going to stop. So basically, if dp of I is true, then we can break out of this for loop and then move on to the next index. So we're going to start basically at the last index, keep going until we've gotten to index 0. And then once we've done that, we know we can actually return that. And that's going to be stored in dp of 0. So believe it or not, that is the entire code, about 10 lines, I think, and this is a pretty efficient solution, as you can see. Hey everyone, welcome back. Let's solve another problem today, longest increasing subsequence. And this is another tricky dynamic programming problem, and I'm going to show you how to go from the recursive solution to the dynamic programming solution. So we're given an array of numbers and we just want to return the length of the longest increasing subsequence. And if you don't know what a subsequence is, it's basically like, let's say this is our input array. We're basically taking a subarray, but that subarray does not have to be contiguous. So like we have from here, so subsequence is 3, 6, 2, 7. Basically, we took this subarray and we removed 1, 2 from it, and we removed a 1 from it. And now it's 3, 6, 2, 7. But you notice about this subsequence, it's not in increasing order, right? We have 6 and then we have 2. That's not increasing order. So this is not a increasing subsequence. So in this example, we're given about 9 elements and we want the longest increasing subsequence, which we see is this. And so how did we get that subsequence? Well, you go from 2 all the way to 101, but you notice that unfortunately this is not in increasing order. We have a 5 and then we get a 3 right after. So we actually have 2 choices. If we remove the 3, we have an increasing subsequence. If we remove the 5, we also have an increasing subsequence. But we just care about the length, which in this case is 4, so we return 4. So the first idea you might have is brute force using depth first search. So let's say that this is our input array, so we have 6 elements. If we want to know the brute force, meaning we want to generate every possible subsequence, we have a choice for each value, right? So for the first 0, we have a choice. Are we going to include this 0 in our subsequence, or are we not going to include it in our subsequence? So in reality, for each value, we have 2 choices. Now, when we get to the next value, we also have a choice. Are we including it or not? So again, we have 2 choices if we want to generate every possible subsequence. So we do that for every single value, and then we see that there are actually 2 to the power of n possible subsequences, where n is the number of values given in our input array. So already you can see the time complexity is not going to be great, but can we take this brute force approach and then somehow modify it to get a better solution like n squared? So let's look at another example, and this time we're going to do depth first search with caching, and we're going to see how that improves our time complexity. So we have an example of 4 elements. So it's kind of obvious that this is our longest increasing subsequence. So the result is going to be 3 elements. But how can we do this with an algorithm that's efficient? Well, let's start out with the brute force approach. Let's check all subsequences starting at index 0 and then repeat that starting at index 1, starting at index 2, and starting at index 3, right? So these are the indices. So we take one decision to start at index 0. We take one decision to start at index 1, one decision to start at index 2, and one decision to start at index 3. So in these cases, these are going to be the subsequences we have so far. So we know index 0 has value 1, index 1 has value 2, index 2 has value 4, index 3 has value 3. So now let's go along the first path, so index 0. So we know if we start at index 0, we have 3 values that come after it. So we can try all 3 of these possible decisions. So we can go along index 1, index 2, and index 3. And we see that all 3 are possibly valid because all 3 of these values are greater than 1. So we can continue these subsequences. So we know index 1 has value 2. Index 2 has value 4, so we can add a 4. Index 3 has value 3, so we can add a 3 to our subsequence that originally was just 1. So now we took index 0 and index 1. So for here, we only have 2 indices that come after these 2 values. So let's continue our decisions. We see that both 4 and 3 are greater than the last value in our subsequence, which is 2. So we can choose both of these decisions. So if we take index 2, then we can add a 4 to our subsequence. If we take index 3, we can add a 3 to our subsequence. So now let's continue here. We have 3 values so far in our subsequence. And there's one index that comes after 2, index 3. It has a value 3. So can we add a 3 to our subsequence? We'll get 1, 2, 4, and then 3. But this 3 is not greater than the last value in our subsequence. So we technically cannot make this decision. So we cannot continue to increase this subsequence anymore. So we can mark this as reaching its limit. We cannot continue it anymore. What about this one? Well, it stopped at index 3, which was over here. So are there any elements that come after it now? No, there's not any elements. So this subsequence has also reached its limit. So we cannot increase it anymore. But so now let's focus on this caching part. What kind of repeated work have we eliminated? Well, let's just do this out of order. Instead of doing these first, let me show you what happens if we try to extend the 3 now. We try to get another element, right? We started at index 3, but we know that no values come after index 3. So this one cannot be continued. But what do we know about index 3? If we start at index 3 and we want the longest increasing subsequence, we just get a single 3. So that tells us that LIS starting at index 3 is 1. We don't need to repeat this work. And isn't that what we just learned over here? Even though this subsequence is length 3, we are talking about starting at the 3, and we noticed we could add a 3 to it, right? This was the element that we added, but as soon as we added that 3, we could not increase this subsequence anymore, right? That's what this X tells us. We were only able to add 1 element if we start at index 3. And that's exactly what this 2 told us as well. If we start at index 2, we can add a 4, but this 3 that comes after it cannot be added. We cannot include that, and there aren't any more elements to add. So as soon as we finished this and we found this X, meaning we could not go any lower, we knew that the longest increasing subsequence starting at index 2 is also 1. So therefore, if we start at index 2, we cannot go any lower. We cannot continue this. And we don't even have to attempt to do that. And what about this branch? So if we started at index 1, we would start with the subsequence of 2, right? That's what this tells us. And so now I'm going to do some more stuff, right? I'm going to choose the next indices 2 and 3. But wait a minute, do I actually have to do that? Because look over here. we started with index 1 and we already did that. So when we started with index 1, we saw we had two choices, a 2 or a 3 index, right? We could choose this or we could choose that. We saw both of them ended, right? We could not continue either of them. So if you want the longest increasing subsequence that starts at index 1 over here, no matter what you choose, the subsequence is going to be length 2 either way, right? Because if we start with a 2, then we can add a 4 or we can add a 3, but we cannot add both of them. So we can mark the longest increasing subsequence starting at index 1 to be length 2. So we actually don't even have to go down this path once we already go down here, because it's just going to be repeated work. And we also see for these two trees that we have not finished yet, once we add a 4, the longest increasing subsequence at index 2, which is where 4 is at, is going to be 1. So we cannot continue this anymore. Similarly, once we add a 3, we know no values come after it. The longest increasing subsequence starting at index 3 is just 1. We cannot increase this anymore. So when we finally in our depth first search get back to the root, we're going to see that the longest path is one of these, right? Either that, or of course you could go down this direction, but either way, the longest increasing subsequence starting at index 0 is going to be 3. And so when you look at these 4, right, because these are our subsequences. These are the longest subsequences starting at each index. The greatest one is 3. And so therefore the result is 3. But now if you actually want to do the dynamic programming solution, you might notice how we're doing this recursively. We're kind of starting at the last index, right, 3, and then working our way up backwards to 0. So then going back here. So can we use that to do dynamic programming? So now let me show you the dynamic programming solution, and it's actually easier than you might think. So we're going to start at the last index 3 and then work our way backward. So we know this is kind of the base case, right? No values come after it. So the longest increasing subsequence we could make from here is just going to be length 1 anyway. So we can say the LIS starting at index 3 is just 1. That's the max length. Now, how do we get the longest increasing subsequence starting at index 2, which is just 1 shifted to the left? Well, one possibility is just 4 by itself, right? So that's one possibility. It could just be 1, or it could be 1 plus the longest increasing subsequence starting at position 3. And what this means is if we take both of these, right, because LIS of 3 is just 1, right, so 3 by itself, but we're only allowed to do this if the value nums at index 2, which we know is 4, is less than nums at index 3, which we know is 3. Is this true? This is not true. So we are not allowed to do this. So normally we would take the max of these two values, but we know that the condition to take the max of this does not satisfy. So we only have one choice, 1. So the LIS of this is going to be 1. I'll put it over here like in the corner. So again, we're going to work our way backwards. So let's get the longest increasing subsequence 1 index back at index 1. So we're going to do the similar thing that we just did. So we know we could take a subsequence 2 by itself, right? That's one choice. 1 is a choice, length 1. We also have a choice, 1 plus the longest increasing subsequence starting at 4. And we're allowed to do this because 2 is less than 4. So it is increasing. The subsequence is increasing. So another choice is 1 plus LIS of 2. And another choice is LIS starting at index 3 because 2 is less than 3, right? 2 is less than 3, so the subsequence is in increasing order. So 1 plus LIS of 3. Now we know that this is 2, and this is 2, so it doesn't really matter which one we do. The LIS of 1 is going to be equal to 2 regardless. So now we want the longest increasing subsequence starting at index 0, and we're just going to repeat what we just did. So we could take 1 by itself, which is just 1, or we could take 1, add it with the longest increasing subsequence starting at 2, or this longest increasing subsequence starting at this index or this index. So we know we're going to get 1 plus 1 from here. We're going to get 1 plus 1 from here. And we're going to get 1 plus 2 from here. And we're allowed to do all of these because you notice 2 is greater than 1, 4 is greater than 1, and 3 is greater than 1. So they are in increasing order. So then we know that the longest increasing subsequence of this is going to be equal to 3, which is what we want. So this is a much better solution. The dynamic programming solution is much better than brute force because the time complexity is O of n squared. But why is it O of n squared? Well, you see we're working backwards. We start at 3 and then we check every position afterwards, which is not too bad, right? So then we iterate through basically every value here. When we start at 4, we have to look at every value that comes after it. There's only one value that's good for us. So we iterate through these 2 values. When we start at 2, we have to check these subsequences starting at these 2 values. So then we have to end up iterating through 2 and every value that comes after, and we do the same thing for 1. So we iterate through 1 and every value that comes after. So you can tell by looking at this pattern is similar to an n squared pattern. So now let's finally write the code. So we know we're going to do this dynamic programming style. So let's have a cache or a list. It's initially going to be set to 1. Every value is going to be set to 1. It's going to be the length of the input array that we're given. So every longest increasing subsequence starting at every value or every index is initially just set to 1. We're going to try to find what the max is. So we want to iterate through every index in the range of our input array, and we want to do it in reverse order. So that's what I'm going to do in Python. If you're not familiar with Python, this might look a little weird, but basically what I'm doing is starting at the last index and then going all the way to 0. And just like I showed in the example, we're going to start at index I, like this could be I, and then we want to iterate through every subsequence that came after it. So I'm going to have another nested loop for j in range. So starting at I plus 1 and then going to the end of the input array. And before we can update LIS, we want to know, is the value at I actually less than the value at j? Because j comes after it. If we want this to be an increasing subsequence, this condition has to be true. And only then are we allowed to update the longest increasing subsequence at index I. And we can set it to the max of itself or the max of 1 plus the LIS starting at j, because we know for sure j is going to be in increasing order with I. And literally that is it. We made sure to evaluate that it's an increasing order. We did it backwards. We made sure to cache the repeated work. What do we have left to do? Well, we want to return what the max is. How can we do that? Well, in Python, you can just take the max of a list. So whatever the greatest value is in here is going to be returned. And so this is O of n squared, and there actually is a better solution, big O of n log n, but I really doubt your interviewer is going to expect you to get this on your own without a hint. If they do, I would personally just walk out of the room. But I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve partition equal subset sum. So this is a pretty interesting problem. So we're given a non-empty array of nums containing only positive integers. We want to know if the array can be partitioned into two different subsets such that the sum of each of the subsets is exactly equal. Notice how that's basically saying if we can take one subset of the array, which is going to equal half of the sum of the entire array, right? Because if we partition it into two equal halves, right? Let's say the total sum was 22. If we partitioned it into equal halves, then each of the halves would be exactly 11, right? AKA one of the partitions is going to be half that of the total sum. So for example, in this problem, the sum is exactly 22. So we want to know, can we get a partition or can we get a subset of this array? Basically, we can choose any of the values and can we get a subset such that it sums up to 11? In this case, the answer is yes. It's true because we can take, the single 11, that sums up to 11, right? And obviously, if there's one way to get half of the sum of the total array, then the remaining elements are going to basically equal 11 as well, right? So you can see that 1 plus 5 plus another 5 is going to be equal to 11, right? Basically, these are the two partitions. So as with many problems, let's just try to figure out what the brute force solution would be. So basically, let's start at the first element, right? And for every single element that we visit, we have two choices, right? We can either include this in our sum or we can not include it in our sum. And we want to basically determine every single sum that we can make with any single subset from this given array. And we want to know, does that sum ever equal 11? Because 11 is our target, right? If we sum this up, divide it by 2, we get 11. So we want to know if that's possible. So let's brute force it, right? So the first choice, we can either choose a 1 or choose nothing, right? Basically skipping that. So either our sum will be 1 or our sum will be 0 because initially our sum is 0. So the next value is 5, right? So basically for each of these paths, we can choose 5 or not choose 5. If we do choose 5 here, we'll get a 6. If we don't, we'll stay at 1. Otherwise, on this path, if we choose the 5, we'll get a 5 because we started at 0. So if we skip the 5, we'll stay at 0. Next, we get an 11. So basically continuing that, right? So I don't know if I'm going to have enough room for this. Okay, no, 11 plus 6 is going to give us 17 on this path. Clearly, we went over, so we would probably not want to continue down this path. But over here, if we skip the 11, we'll get a 6 still. If we take 11 here, we're going to get 12. If we skip it, we'll get 1, and etc., etc. We'll get 16 here, skip, we'll get 5. If we take 11 here, we'll get 11, skip, get 0. But clearly, we found our target that we were looking for. We don't really have to continue anymore, right? So basically, we can skip this last element. We found our target. We're going to return true, and we're going to go back up. So as you can tell, since every level of our decision tree, we're having two choices, right? And what's the height of this decision tree going to be? Basically, for every single element, right, we're going to have a decision. So let's say the input size of the array is n. So basically, our time complexity is going to be 2 to the power of n if we do a brute force method. So let's go back to the first step, basically the first element that we were at, and let's see if there's any repeated work that we can cut down on. So initially our index or our I pointer is at the first element, right? So basically we're at the beginning of the array. We can go down the entire array. We can choose any elements from here, and we want to know, can we sum up to the target 11? Now, once we take our two paths, right, we're basically going to say I is now going to be shifted to the next element, 5, right? And we had two choices. We could have either chosen the 1 or we could have skipped the 1, but clearly now we have a new subproblem. We already have a 1, so from the perspective of this decision, we're not looking for a target of 11 anymore, right? We're looking for a target of 10. We're looking for a target of 10, and not only that, but initially our I pointer was here, meaning we could have done the entire array, but now our I pointer is over here, so we're not even looking at the entire array anymore. We're looking at a subarray, basically the remaining elements of the array minus this first one. So if we were to cache this, our new subproblem would be target of 10 that we're trying to solve, and I is not at 0 anymore. Index is at 1. Similarly over here, we can see since we're at 0, the target is still 11, right? We are trying to sum up all the way to 11, but the index that we're starting at in this case as well is 1 now, right? Because we basically said we were skipping this element down this path, right? So now we want to know, is there a way that we can sum up to 11 basically just from this subarray, right? And every time we made a decision, we would continue to update these values, target and I, right? So as you can see, what are the dimensions of our cache going to be? If these are the two variables of our cache, what are the dimensions going to be? Well, clearly I could be any value in the input array. So the dimensions of our cache are going to be n, where basically n is the size of the input array, right? Because I could be at any value from 0 to n minus 1. And what about the target? Well, the target is basically the sum of the entire array divided by 2, right? So basically sum of nums divided by 2, or, the constants usually don't matter in time complexity. So basically this is going to be the big O time complexity. Now this is technically better than 2 to the power of n, because they do give us a pretty good limitation. Like the values in this input array are usually going to be, I think, less than or equal to 200. Now, if they were really big, like if this could have been 1,000,000, clearly that would not be very efficient because our sum could have potentially been super large. But this is basically the best way that we can optimize it. So basically, if we did a depth first search solution with a cache, like a backtracking solution with a cache, this would be the time complexity, and this would also be the memory complexity, because this would be the dimensions of our cache. But it's actually possible to improve the memory complexity a little bit with dynamic programming, and the time complexity is mainly going to stay the same as this, but the overall memory complexity can be improved. And let me show you why that's the case. So suppose we were starting at this first value, right? And let's say we already knew all the possible sums that any given subset from the remainder of this array. Like basically what we could do is say for every single one of those sums, we would add 1 to it, right? So for every t, let's just call it t for now, in that subarray, we're going to basically be checking 2 things, right? Either if t is equal to target, right? Like some possible sum from this subarray totaled up to the target, then we would return true, right? Every possible sum that we could create from any subset in this subarray, and if it basically that's what t would be. And if that t happened to be equal to the target 11, then we would return true, right? Or if we took every single sum we could create from this subarray and added 1 to it, basically 1 because that's the only value left over here, right? 1 plus t equal to target. If that was also equal to 11, then we would return true as well, right? So basically, this is the recurrence relation that I'm trying to show you. And so this is basically the idea we're going to use for the bottom up solution. So instead of starting here, we're going to work our way backwards. So we're going to start here. So, and this is very simple, right? So how many possible sums could we create from this subarray? Well, there's only one value here, right? We either take it or we don't. So the amount of sums we can create is going to be 0 or 5. And what I'm going to do is I'm going to be storing these values in a set. So let's say this is our set. So far we have 0 and 5. Next, what I'm going to do is I'm going to go to 11, right? We're going to work our way backwards. I'm going to start at 11 and I'm going to iterate through every single one of these. And I'm basically going to add 11 to them, right? So for 0, let's add 11 to it. That's going to be 11. I'm going to add that to our set. Let's look at 5. That's going to be 11. I'm going to add that. 11 plus 5 is 16. I'm going to add that to our set, right? Clearly, we can see we already found the target value, so we could return, but let's just keep going to see all the possible targets we could create with this input array. So we were done visiting 11. Now let's go to 5, right? So basically, we're going to iterate through every single one of these, add 5 to them, and then see if that's a new value. If it's already a value that exists, then we wouldn't do anything. Like in this case, we can see 5 plus 0 is just going to be 5, right? So I'm not going to add a second 5 to this because we already have a 5. This is a set. It's going to want only unique values. So we're not going to end up adding a second 5. But if we add 5 plus 5, that's going to be a 10. If we add 5 plus 11, that's going to be a 16. We already have a 16. If we add 5 plus 16, that's going to be 21. And basically, I'm going to do the exact same thing with 1. So, we would add a 1 here. We'd add a 6. 5 plus 1 is 6. 1 plus 11 is 12. 1 plus 16 is 17. And 1 plus 10 is 11. We already have 11. 1 plus 21 is 22. So basically, this is the entire list of sums we could possibly create from our given input array. As long as this set contains 11, we return true. If it doesn't contain 11, that means it's impossible to sum up to this target, so we would return false. Now, I think in practice, the size of the set is probably going to be about the same size as the cache that we would use in the memoization technique, but technically the size of this cache is going to be limited to the size of the target, which is basically limited by the sum of the nums input array. So this is going to be the memory complexity in this case. Technically, the time complexity is going to be the same. But I think this solution is definitely easier to code. It's just a little bit tricky to actually arrive to this solution. I think going through the brute force to the caching to the dynamic programming solution is the best thought process to arrive to this optimal solution. So now let's jump into the code. So one thing I didn't mention is that if the sum of our input array is odd, then it's obviously going to be impossible to partition it into an equal half, right? So basically if the sum of this modded by 2 is 1, then we're going to return false. Also, I'm going to have a DP set, as I mentioned, because this is going to be the most optimal solution. To the DP set, I'm just going to add a base case of 0. Basically, we're guaranteed that we can add up to a sum of 0, right, if we just don't choose any elements from the input array nums. And the target that we're trying to sum up to is, of course, the sum of nums divided by 2. So with that being said, let's iterate through every single value in nums in reverse order. You could do it in regular order, but I'm just going to do reverse order because I'm used to it. So we're going to go through every target or every total value that's already in our DP set for every t in DP. And what we want to do is to DP add a value, right? We basically want to add t plus nums of I, right? Because I is the current index that we're at. We want to add, for every single t that's already in DP, we want to add nums of I to it, right? But we can't update this DP set while we're iterating through it. So what I'm going to do is create a new DP set, basically next DP. It's going to be the DP set that we iterate through over the next time we execute the loop. So instead of adding to DP, what I'm going to do is add to next DP. But we also don't want to lose all the original values that are in DP. So what I'm also going to do is to next DP, I'm going to add the t value as well, whatever the t value happened to be. Now, if I really wanted to, I could probably skip this line if I just took DP and cloned it and then set that to next DP, but whatever you prefer. Basically what I'm doing is I'm setting next DP, I'm taking every value in DP, adding it to next DP, and also adding this t plus nums of I to next DP. And once this loop is done executing, we're basically going to update, reassign DP to the next DP set. And this is going to keep executing. It's going to keep executing. I is going to start at the end. And it's going to go all the way to 0. So then we're going to have gone through every single one. And at the end, we can return true if and only if the target happens to exist in DP. Else, we have to return false. And yeah, so this is the entire code and it runs fairly efficiently. So this is about 50%. Now I think it would probably be a little bit faster if, the first time we find the target value, if we just returned it. Actually, let me just, you can probably stop watching at this point. That was the entire solution, but let me just see if this actually does speed it up. So let's say if I happens to be equal to the target, we can immediately return true. Let me see if that does speed it up. Okay, so that actually did. So it's about twice as fast. I think the old one was 14 milliseconds, so this is 600 milliseconds. So this might be an optimization that your interviewer would like, but the overall time complexity is still the same.